Test, test. Nice.
Okay, thank you all for coming. And sorry about the delay. There was a trouble on everything. So let's start the first talk of this session. This is about contract satisfaction proofs and presented by Arthur Collinson.
Thank you so much. So I'm Arthur, and indeed I'm going to be talking about contract satisfaction proofs. This is joint work with Howie and Jana from MPISP. Okay, so the motivation behind this work is microarchitectural side channel attacks. And the context is that we have a program that we would like to execute on a CPU. And this program might manipulate all sorts of data, potentially some of which are secret. And the question we're asking is whether a potential attacker can recover secret data just by observing the CPU. And unfortunately, the answer is yes, via microarchitectural side channel attacks. And examples of such attack have been beautifully demonstrated over the past 10 years. And you might have been familiar, or you might have heard about the Meltdown and Spectre attacks, for example. Okay, so the big question is, how do we defend against such microarchitectural side channel attacks? And one key idea is to verify that a specific program is secure to execute on a potentially vulnerable CPU. So the big idea is that we want to prove that executing a certain program on a certain CPU cannot leak private data. The problem is that, as I said before, those security vulnerabilities, they're coming from the microarchitecture. So if we want to prove this, it means that we need to reason about the way the CPU is executing the program at the microarchitectural level. And this is very tedious. So there is a solution, which is to use so-called leakage contracts. The big idea is to introduce a layer of abstraction in the middle, called a contract, which is going to approximate the leakage behavior, and we're going to prove security with respect to the contract rather than a direct proof with respect to the CPU. The big benefit of doing so is that hopefully the contract is describing leakage at a higher level of abstraction, typically at the ISA level, which makes verification much more tractable. But there is a catch. Of course, for this to work, it is crucial that the contract is faithfully approximating the actual leakage of the CPU. And this is sometimes called contract satisfaction. What we want to prove is that if we have a security proof with respect to the contract, we must be sure that executing the program on the actual CPU is also secure. And if we want to reuse the contract multiple times, ideally we would want to prove that for any program. And this is exactly the focus of this talk. How do we prove this contract satisfaction property? So existing approaches so far are either doing pen and paper proofs. Some people have tried to do testing directly against CPUs. Some people have tried hardware model checking approach. And the question we're asking today is, can we also add like another level of guarantees by mechanizing those proofs in an interactive proof assistant, like for example in ROC or in Lean? And the short answer is yes, we tried, but a naive approach turns out to be quite tedious without formal foundations. So we're presenting two contributions. The first one is a principled, sound and complete proof technique for contract satisfaction proofs, and actually for a more broader class of problems. I'll come back to it in a minute. And this technique is called relative bisimulation. And the second contribution is to present a deductive system to simplify relative bisimulation proofs. Okay, so let's be a little bit more specific. What is the setting? So we suppose that we have the hardware semantics that describe how CPUs execute programs. We have a CPU state. The CPU state has a program. It might have some architectural information like a PC, registers, and it might also have microarchitectural information like caches, branch predictors, that sort of things. We consider that we have like a small step labeled operational semantics that describe how to transition from CPU steps to CPU steps, and that's labeled with attacker observations that model what an attacker can observe in between the execution step of the CPU. And we're interested in collecting observations an attacker can make by observing the CPU starting from a given state. Okay, so with this setup in mind, what we are interested, or gold standard, is to prove non-interference. It means that if we take a pair of states that have the same public data but potentially different secrets, we want to make sure that we have the same observation. An attacker cannot distinguish those two states during the execution. So said otherwise, possible observation should be completely independent from secret data. So of course, proving this directly is very complicated because, as I said before, this property mentions the microarchitectural details of the CPU. And proof engineers don't want to look at that. So the idea is we introduce contracts. And what are contracts formally? They're basically just another label semantics. Just this time, the states do not mention the microarchitectural details. And we're going to try to predict the leakage instead of giving the actual observation an attacker can make, which we cannot because we don't have microarchitectural states here. OK, so as for CPU semantics, we are interested in traces, like collecting the predicted leakage over time. OK, so how do we use contracts to prove non-interference? The goal was to prove non-interference with respect to the CPU semantics, but we are not going to do that directly. Instead, we're going to split it in two parts. The first part is that we're going to use the contract as a drop-in replacement for the CPU semantics and prove non-interference there. This is nice because we don't have to talk about microarchitecture anymore. But of course, this only works if we have some sort of guarantee about the contract. And in particular, we're interested in proving that if we have equality of trace at the contract level, then we must have equality of trace at the hardware level. And it's relatively easy to see that if we compose, by transitive of implication, if we compose those two parts, then we obtain non-interference with respect to the CPU. OK, so let's dissect a tiny little bit this contract satisfaction property. In a nutshell, what it says is we need to prove trace equality under a certain semantics, namely the CPU semantics. But we get to assume, to prove that, we get to assume that we have trace equality under a second semantics, namely the contract semantics. And ideally, we would like to do that for any program P. So how to do that? If we look a little bit more closely and we focus on the rightmost part of the implication, this essentially boils down to proving trace equality. And we do know how to prove trace equality. We just do a proof by B simulation, right? It's that easy. Except it doesn't work because we don't have any assumption about the initial states. We cannot guarantee, like out of the blue, that those two traces will be equal. There is no reason to believe that they will be equal. So in practice, we actually really need to exploit the contract to prove trace equality. And this means that vanilla B simulation will just not do the trick. So the key idea is to lift B simulation, which is a binary notion, to a relative notion of B simulation, which is a 4RE notion. OK, so before I explain how to do that in a little bit more details, I want to emphasize that the general problem we're looking at is relative trace equality. We have 4 traces, and we want to show that assuming equality between the first 2 traces, we can prove equality between the second 2 traces. And it turns out that it's a very recurring theme in PL and in security, and maybe in other fields. So it shows up in secure compilation, in relative security proofs. And if you have other instances, please come talk to us. We are very interested. OK, so one of the big problems when trying to prove this property is that we have 2 traces or 4 traces coming from 2 different semantics. There is no reason to believe that they're perfectly aligned or perfectly synchronized. And in particular, it might very well be that to prove an equality between the second 2 traces, we need to exploit an equality that happens at a much later point, for example, in the first 2 traces, and vice versa, by the way. OK, so how do we do that? We introduce relative B simulation. I'm not going to give you the full technical details because it's 11 in the morning and I don't want to bore you. But I want to emphasize a key feature, which is that internally, relative B simulation is a nested co-inductive inductive definition. And the intuition behind it is that the outer greatest fixed point, so the co-inductive part, is here to establish equality between the 2 hardware traces. And the inner least fixed point is here to exploit equality between the contract trace. And the alternation allows us to do that in an asynchronous manner. OK. A big theorem is that it turns out that this is a sound and complete fixed point characterization of relative trace equality, which is great because since it's a fixed point based definition, it means we can prove relative trace equality by co-induction induction. So this is all great in theory. I don't know about you, but personally, I really do not like to stare at fixed point equations. What I do like, though, is nice high-level proof rules and deductive systems. So let's do exactly that. Can we use relative B simulations in a much more like user-friendly manner through a deductive system? So at its core, the deductive system we propose is operating on so-called proof quintuples. On the left, we have a pair of contract states. on the right, we have a pair of hardware states, and on the left of the turnstile, we have a relation R that's essentially a candidate relativity simulation. You can think of it as a set of quadruples that we assume to already be relatively dissimilar. The catch is that this hypothesis is guarded, which I'm representing using like a solid box around the R. And at some point during the proof, it will become unguarded. And when this happens, we can exploit the assumption. This is actually reflected by the first rule of the deductive system, which is called the cycle rule. And that says that at any point in time, if the hypothesis is unguarded, we get to use it and finish the proof. So the whole game is to get to this point. How do we do that? We do that using the hardware step rule that enables us to unfold one hardware step from the current quadruple of states. And if we manage to prove equality of observation just for this one hardware step, then we get access to the hypothesis and the proof resumes with the successor states. Okay? So kind of symmetrically, we have the contract step rule that says that we can unfold one contract step. And this time we get to assume equality of leakage, and the proof resumes. The catch is that this time it keeps the hypothesis guarded. And the intuitive reason why, it's because this proof rule does not really prove anything, right? We are not making any progress. There is no side condition that we need to check. It's just generating new assumptions if we need them. Okay, so we've seen how to get access to the context, how to use the context, and how to generate new assumptions in an asynchronous manner. But the big question that is left is how do we store new things in this context? How do we extend our hypothesis for later use? And we do that using a co-induction rule that says that at any point in time, if we know that the quadruple of state we're looking at satisfies a relation R prime, we get to store this R prime in the hypothesis for later use. The catch is that the proof resumes, but from an arbitrary quadruple of states satisfying R prime, not the previous quadruple of states. You can think of this rule as a rule to establish incrementally a relational invariant. Okay, so that's actually about it for the deductive system. It's only 4 core proof rules that I find to be relatively simple and intuitive. It turns out that those 4 rules are giving us a sound and complete proof technique for relative trace equality. So in particular, we can prove that if a quintuple is derivable starting from an empty context, then this is equivalent to proving relative trace equality. Okay, unfortunately, in the interest of time, I cannot really give an example. It would require kind of a lot of setup, like giving 2 semantics and so on and so forth. But we did apply this deductive system to 2 challenging contract satisfaction proofs. The first one is a sequential contract that's essentially approximating out-of-order execution by sequentializing everything, and an always mispredict contract that is typically used to approximate branch prediction in modern speculating CPUs. I don't want to give too much more details, but I do want to mention that for both examples, the asynchronous handling of contract and software steps, hardware and contract steps, sorry, was absolutely crucial. Without this feature, the proof do not go through. Okay, so there are additional features beyond the 4 proof rules that I discussed. In particular, we can further equip the deductive system with so-called up-to techniques to exploit symmetry and transitivity and simplify proofs dramatically. We also support weak traces, so a setting where some of the transitions might actually not be labeled with an event. And in that case, we can do pure asynchronous reasoning where every one of the 4 state progress independently from the 3 others. This is sometimes very useful. If you want to know more details about how the proof system works, or if you want to see example, the paper is already out. And if you're a fan of ROC proofs, please look at the ROC development. It is already relatively exhaustively documented. And with that, that's the end of the talk. And if you have any questions, I'd be very happy to answer them.
Thank you. So it's now time for Q&A.
Case studies at the end, it sounds like you're dealing with models, not actual synthesizable hardware designs. And when I think back to the 2-step decomposition you put up there early on, 2 different, one equality and one quantified equality. What really struck me in the second property was that it quantifies universally over all microarchitectural state.
Yeah.
Implying that at any point in the kind of abstract execution, you have to be able to has to like make sense to continue with arbitrary microarchitectural state, even though that state might in general be dependent on the architectural state. So that seemed kind of weird. And then also, in general, I think you'd be concerned about cases where the two executions you're comparing, they have different microarchitectural state, but some reasonable equivalence relation connects those two together. So I'm just wondering, would you run into obstacles through the design choice you made that doesn't seem to directly handle either of those complexities?
Actually, you're absolutely right. This does not really matter in practice because you can very much add any assumption as you want, right? You can refine your assumption and start from states that are further constrained. Like relative simulation still applies, the deductive system still applies, so that would still work. And regarding your first remark, yes, we are working with models or very simplified models of CPUs, but the beautiful thing is that if you come up with a slightly more precise, slightly more realistic model, you can still compose the proofs, right? By transitivity, you can compose multiple relative simulation proofs and get the whole chain. So you can incrementally refine and go closer to like a more realistic model. So I hope this answered the two questions.
Yeah, thank you.
Any other questions? We started late, so we can use time. I just want to ask one question. So is the use of R can be understood as a kind of instance of parameterized co-induction?
Yes. Yes, exactly. So internally, we're heavily using parameterized co-induction, and we're actually even using generalized parameterized co-induction because we need it for the up-to techniques. Yes, that's exactly.
I see. Any questions? Okay, if not, let's thank the speaker again.
Oh.
So next talk is about sparse tensor program optimization, and the presenter is Amanda Liu.
Great, thank you. Awesome. So to start us off, I'm going to talk about sort of in these high performance domains like visual computing, scientific computing, physical simulation, and of course, machine learning. These programs are often written as pipelines of tensor operations. So you're going to have things like matrix multiplies, convolutions, stencils, and the like. And these operations usually involve performing some sort of mathematical computation over the entries of input tensors, and also returning the output in the form of some other rank tensor. And often these high-level tensor expressions are computed at the low level in some form of imperative loop nest array code, so roughly in a form like so. We're going to have a nested for loop structure binding iterating indices. So here they are I, j, and k. And the body of the loop nest is going to be some function e of those indices. And this is going to be the actual scalar computation that's being performed between the entries of the input arrays. And then the computed value is stored or possibly reduced into an output buffer at some offset at the bottom of this loop nest. And this offset is also computed as a function of the iterating indices described by f here. And this structure in an array program establishes two important things. One is the compute order. which is determined by the structure of the nests and the order in which I, J, K are introduced, and therefore how the indices change relative to each other. And this is also the order in which E is going to see these indices. It also establishes what we call the storage order. So this is where those computed values get written into memory. And this is determined by the storage index expression described by F. And navigating a trade-off space to optimize array programs often boils down to being able to manipulate relative compute and storage order in these loop nests. This, in part, motivated how we designed ATL, a domain-specific tensor programming language. The language itself is a pure functional high-level language meant to allow us to express tensor programs in simple mathematical terms. So the language itself includes scalar expressions that involve arithmetic expressions as well as tensor access. The rest of the core of the language contains constructs that allow us to build up tensors and compute using these scalar expressions. And notably, we have the big operator constructs of tensor generation and tensor summation. And to get a better sense of these constructs, here's a small example ATL program expressing matrix vector multiplication. So ATL contains what we call the tensor generation construct, and it works a lot like a list comprehension. So it lets us define a tensor element-wise. So for each index I, the element is going to be the value of the body expression evaluated at that specific index. And the index I is going to range from 0 inclusive up to n exclusive. Similarly, there's a summation construct, but instead of generating a tensor with these elements of a function of I, it's going to sum these elements. And of course, we have the tensor access and scalar operations such as multiplication to allow us to express a simple matrix vector multiplication program here. We refer to these core constructs like tensor generation and summation as iterating constructs since they bind these index variables, and when they are lowered, they correspond to for loops. And as a result, these constructs establish the compute order of a tensor computation at a high level. Aside from these core constructs, the ATL language also contains a separate set of constructs we call reshape operators. And each reshape operator corresponds to a common natural tensor transformation like flatten, which combines the top two dimensions of a tensor row-wise, or transpose, which swaps them. And during the lowering process, these constructs affect the storage order of the program, or in other words, they're going to change the storage index expression generated at the bottom of the loop nest. And the ATL scheduling framework allows us to optimize programs source to source via a series of scheduling rewrites, which are theorems of equivalence between ATL terms that have been proven in the ROC proof assistant. So the scheduling script applies a series of these rewrites, taking us from one program to another, traversing a space of equivalent programs. So to optimize programs by manipulating relative compute and storage order in a verified semantics preserving way, we also introduce operators using scheduling rewrites. So we introduce reshape operators in pairs via what we call adjoint theorems, where when they compose, they form the identity. So this means we optimize programs by pulling a neat little trick. We're going to start with a simple, straightforward description of a tensor program in its most natural sort of mathematical core ATL form. And then we're going to rewrite to introduce an adjoint pair of reshape operators. In this case, it's R and its right inverse. We then are going to unfold one of these operators, inlining its definition. And so inlining a definition will often introduce more core ATL constructs like tensor generation show here. So inlining this operator is going to change the compute order of the program being expressed. And leaving the other reshape operator in place is going to inform the compiler to generate the compensatory storage reordering. So the end result is you get a functionally equivalent tensor program, verified to be functionally equivalent, but we're able to change the order of computation and storage into a pattern that could be more efficient for a particular program if we've made a smart choice of R. So all of that stuff has actually old hat. The existing ATL work covers this, but the existing ATL work has primarily been focused on supporting computations over dense array representations. So this is where each element that exists logically in the tensor also exists physically, and it's stored basically contiguously in memory. But in the real world, a lot of tensors we compute over are massive, meaning they probably don't fit into memory, or their outputs would not fit into memory. And they are largely sparse, meaning nearly all of their values are actually 0. So sparse formats allow us to compress away some or all of these zeros into a more compact representation, so you can more easily compute over these smaller structures. For example, a compressed sparse row, or CSR, is a common matrix compression format. So the way it works is you take the elements of each row of a matrix and you remove the zeros, and you maintain the original coordinates of these surviving elements in a corresponding array. So they basically sort of line up here. What you then do is you concatenate these coordinate and data arrays from each row. So now you have two arrays, one of the integer array containing your coordinates and the other one containing your compressed payload. And from there, we now construct a third array called the position array that tells us where to slice into the underlying arrays, because we've sort of compressed away the row or dimensional separating information. So CSR is represented by these three arrays: a position and coordinate array, and finally your payload data array. And in a way, if we squint at this point, sparse storage formats can be seen as this particularly exotic form of storage reordering. So a format's decompression scheme can be seen as the compute order change, and the compression scheme becomes the specification as to how to interpret the reordered storage. In this case, we can imagine a reshape pair that's called something like CSR to dense and dense to CSR as its own reshape operator adjoint pair. And so we can rewrite a program beginning with a dense ATL program and pull a similar trick to before. But instead, we're going to rewrite to wrap the tensor operand we want to compute over in a compressed format with the compression and decompression routines we want. So in this case, if we want to do CSR, we're going to have to use the CSR-specific reshape operators that I proposed before. And we can replace the call to dense to CSR with the three arrays that we know compressing to CSR are going to produce. And then we can unfold CSR to dense, so we're now looping over these compressed arrays instead of the original dense matrix. And of course, we can continue to simplify and rewrite the resulting ATL program with other scheduling rewrites proven within the framework. So we're able to start with the dense ATL program and derive an equivalent optimized program operating over sparse operands now. But now I probably know what some of you are thinking. Surely there are a ton of sparse formats in the world. Are you really suggesting that we design a new reshape operator pair for each one? And not to mention, we would have to then prove the adjoint identity property for each pair. And this is also not to mention for each dimensionality, like matrices versus a three-dimensional or n-dimensional tensor, et cetera, we would have to extend these definitions and proofs as well. And I would say, you know what? You make a very astute point here. Have you seen the rest of this presentation by any chance? It's true. It would entail a lot of manual work, and it would make it prohibitively difficult for someone who is not familiar with formal verification to write and experiment with new formats. So what we would really like to do instead is to start with an original dense ATL program and rewrite to introduce a compression-decompression scheme, wrapping around the operand we want to compress. But this time, we're going to parameterize the compression function by the format that this tensor is going to be stored as. And not only that, but this format itself is going to be expressed as a list with entries that represent the kind of compression that's going to be performed on each dimension of a tensor. So therefore, not only is this compression-decompression scheme parametric in terms of its format, it's also now dimensionally compositional and extensible. And we want this call to compress to represent the storage reordering, so we can symbolically lift this out into a reference to the stack of metadata index structures that we expect from this list of compression formats. And now we can unfold decompress to introduce, again, whatever loop structure and access expressions that are designated for those types of metadata index structures. So now we can compute over those structures instead of the dense ones. And of course, from here, we can use the existing ATL scheduling framework to perform any downstream optimizations we would like to. And the key sort of to this abstract compositional approach to rewriting sparse tensor formats in a formally verified way is going to be defining this level format abstraction that pertains to the single dimension of compression in a tensor. In particular, we want to be able to define it in a way that is algebraic and rigorous enough for us to prove these formal properties of it and the adjoint pair theorem. So properly defining this is going to be the crux of the work that we're going to be showing here. So we define an abstraction for a sparse level format by its metadata index structure type and the actual function to define how to encode one dimension of a tensor into the index structure. And also there are a number of other functions that allow us to translate between physical sparse positions and logical dense coordinates of a tensor and how to build these up in multidimensional cases. For the details of these, you can read the paper. But I think more importantly, the level format abstraction is formal, so it includes these properties that these functions have to uphold so that they actually meaningfully describe how to encode, decode, and interact with the compressed structures itself. Likewise, these properties are quite detailed, and I'm not going to spend too much time on them. If you're interested, I recommend looking at the artifact or possibly the paper. And the key is that with these functions provided by the abstractions interface, we can define the compression and decompression function that I showed before in a way that is dimensionally compositional and format agnostic. So in the definitions itself here, we never have to case over what F is, or we never have to case over the formats within F. We simply recurse over the length of this format list to accommodate higher ranked tensors. And similarly for decompress, the metadata structure list M now contains all the type information as to how to decode a given format. No manual casework has to be done. And using these definitions now, the properties enforced in the level format abstraction can be used to prove that the compression and decompression pair is indeed an identity adjoint pair. This means that if we expand the sparse format library in the future to accommodate new compression structures and formats, we still only need to prove the soundness theorem once and for all. So what we did is we proved 5 instances of this level format abstraction. We proved dense, which just keeps every element of the tensor in a dimension. We also prove a format called compress, and this refers to sort of the row level compression we did for CSR. We also support bitmask, which maintains in storage each tensor element, but also contains the bitmask for that dimension for each positional argument that is 0. We have hash, which stores each non-zero element in a hash location along with its original coordinate in a fixed size hash array. And finally, we have scalar, which is a trivial level format that is only applicable on compression calls to 0 ranked tensors. But this format is included just so that the base case of our dimensionally compositional definition is well formed. And now this isn't a large number of supported formats, but this is actually quite favorable since implementing a new level format is the only time where you need to provide new function implementations and new format-specific safety property proofs. So using just these concrete format instances, we can build up a large number of multidimensional formats compositionally, essentially for free. And indeed, with just these 4 non-trivial instances, we can recover a large set of existing common idiomatic tensor formats, including CSR, by simply composing them in a list as the format argument we pass to compress. And not only that, we can express more these sort of rich sparse formats as well when we interleave them with reshape operators. Formats that you wouldn't think could be expressible in this paradigm due to the fact that there are dependencies over indices in neighboring dimensions. And that those dependencies affect how an element is going to be stored after compression, since levelization kind of forces us to box out and separate concerns, isolating one dimension at a time. But reshape operators allow us to get around this, which is especially cool, I think, and makes a lot of sense when you consider that we're framing compression as a storage reordering, and our reshape operators were ATL's original set of storage reordering combinators. This allows programs to design very easily and customize formats for any dimensionality with formal guarantees of correctness and no proof or implementation overhead. We evaluated this framework against Taco, the sparse tensor compiler, across a number of kernels and sparse formats using a combination of real-world sparse tensors and also synthesized sparse tensors of different sparsities. And here, the horizontal green line across all of them represents Taco's throughput, and the blue bars are the relative ATL program throughput normalized against Taco. So the higher the bar, the better here. But we were able to get throughput pretty comparable across the board with a few certain exceptions that I think are actually quite interesting. And if you're interested, you can read the paper or talk with me about it afterwards. We also introduced 2 new sparse iteration constructs into the language so that we can talk about iterating over these structures without having to use for loops for all these procedures. The first construct is scatter, denoted by the cross arrows as a bigger operator, which allows us to take values of E computed within a bound and scatters them, so writes them into an output tensor at a specific scattered index determined by F here. And the second construct is co-iteration, and it's denoted by a big bow tie join operator. And as the notation suggests, it allows us to perform a merge over multiple integer arrays based on some predicate P. And using the co-iteration construct, we're able to derive tensor programs computing over multiple sparse operands and compile efficient execution strategies for them, rather than just naively scanning over them using for loops. And for these multi-sparse operand programs, we also found that we were able to get performance competitive with the Taco compiler as well. So that is all, and I'm happy to take any of your questions.
Yeah, any questions?
Yeah, so really interesting talk. So of course, for dense programs, the iteration order matters because of machine constructs like caches. But for sparsity, iteration order matters even more because it affects the amount of metadata that you have to read for each rank iteration. And so I'm wondering if you can use the fact that you've developed this kind of formalized and very structured representation of the formats to maybe allow you to reason not just about correctness, but also about performance in terms of things like ordering your rank iterations.
Yeah. So I think what you're talking about here is if we were to think about constructing the program and also possibly the format such that the way that compression was performed originally, the iteration structure, you're changing essentially like the order in which you're traversing over non-empty nodes. Is that it?
Yeah, like if you're traversing over a CSR matrix, like traversing over rows first is going to be a lot faster than traversing over columns first, right?
Yeah, exactly. I think part of the way that the framework has us defining these compression formats, it sort of lends to that as the initial iteration order already. It tends to be the most, or however you define your compression routine, tends to be the initial way that the iteration order is generated, but it's true that later in downstream scheduling, you're able to perform rewrites to change the sparse iteration order as well.
Cool, thanks.
No questions? Okay, let's thank the presenter again.
Is it better now? Oh yeah, now I can hear myself.
Sorry, so the next talk is about iris WASM effects, and the presenter is Maximum Lepougou.
Hi everyone, good morning. I'm Max, and today I'll be talking about iris WASM effects. It's a work that's at the confluence of three main topics: the WebAssembly programming language, the iris separation logic, and the use of effect handlers as a programming technique. So let me walk you to how we get there in the middle. The starting point for us today is WebAssembly. WebAssembly is a very unique programming language in that it's both something that's very widely used and cared about. It's not a toy language. It's not a simplified version of something else. But it still has a fully defined formal specification, which makes it relatively easier to do formal reasoning on the language. And so we looked at proving some formal properties about WebAssembly. The thing that we were originally interested about was local state encapsulation, a property that is very cared about in WebAssembly. And what this means is that the code in WebAssembly organized in modules should not have one module A arbitrarily meddle with a module B's inner state. Module B's global variables, functions, memory should not be arbitrarily accessed by module A unless module B has specifically, explicitly tagged an object as being exported. And now the way we've gone about to do this kind of formal reasoning work is by using separation logic, and more specifically the iris separation logic. Iris, if you've never heard of it, is a framework for logic that has an implementation in the rock proof assistant. And the way it then works is if you're able to describe the operational semantics for your language in rock, Iris then gives you a lot of tools and a lot of rules to then reason about programs written in your language. I'll show an example in just a second. And so we wondered if we could use this separation logic to reason about an actual real-world language like WebAssembly, and the answer was yes. We defined Iris WASM a couple of years ago, which is a program logic that helps you reason about programs written in WebAssembly. This is going to look something like what I have over here. My precondition P implies, with this little magic wand, which is our separation logic implication, a weakest precondition on my program E. And what this means is that my program E is going to run without ever getting stuck. And if it ever terminates on a value V, then my postcondition Q holds of that value V. So for example, I've showed here what this could look like for a very simple program that just retrieves the value of a global variable. I have to assume that I have this resource corresponding to my global variable G, imagining that G points to V0. Then I'm able to safely run this program that's just one instruction, get global variable G, and at the end, I will still own that resource corresponding to global variable G, and using this star, which is my separating conjunction, I know that the value that I get back, that I terminate on, is going to be that value V0 that I have in my value G. And so using this logic, we have formally established this local state encapsulation property, which now means that this property that we probably already knew was holding is now formally stated, formally verified. But more importantly, we now have a starting point to reason about new variants of WebAssembly. WebAssembly is a very, very vibrant research ecosystem. New versions are proposed all of the time. And a lot of the time, these new versions can be thought of as WebAssembly where you're adding a new feature. And because Iris is also a very vibrant research ecosystem, that feature has oftentimes already been reasoned about in Iris and is well understood in the world of separation logic. So we thought maybe in those cases you could massage all of these existing works together to get a program logic for your new version of WebAssembly. And I'd like to stress here that even though I'm using this kind of visual with a Venn diagram, this is a lot more complicated than taking just the intersection of existing works. There is a lot of work involved in doing formal reasoning about industrial-sized languages. But we argue that this is something that gives us a lot in return, that we should still see this effort through, because everybody kind of wins something when you do this work. The WebAssembly community gets to have their new versions validated, completed. We can find bugs in some instances, and it's really a useful feature to encouraging adoption of these new versions to have formally verified properties. The Iris community gets to see the logic exercise at an industrial scale, and that sometimes highlights places where the logic should be completed or new needs. The new feature community also gets to see their features studied at a real-life scale with new formal tools being developed. This kind of roadmap to reason about a new version of WebAssembly has already been successfully applied to memory-safe WebAssembly. There is a version for rich WASM that is on the way, and today I'll be speaking of Iris WASM effects, a version of WebAssembly with effect handlers. So for the rest of this talk, I'll introduce WASM effects and our logic with regards to reasoning about programs written in WASM effects. If you've never heard about effect handlers, they're a programming construct that is increasingly popular because it allows to, in specific circumstances, it will allow for a lot more efficient programming. You can think of it as kind of an exception where you would throw back control flow to a handler somewhere higher in the execution flow, but you can then later resume and come back to that point where you have thrown that exception. These are known under a number of different names. Call CC and throw is probably the most common of those. So if you've ever seen that, that is effect handling. Async, await is another way of doing this. In WebAssembly, these are called instead resume and suspend. So the version of WebAssembly with effect handlers that was introduced a couple of years ago introduces a couple of new instructions. Cont new creates a new instruction. Resume runs a continuation that was created with continue, and suspend triggers that effect to throw that control flow back up. I'll show an example just in the next slide. Just before I show this example, I'd like to mention very quickly this last instruction on my slide, switch. I'm mentioning it because it is something that a lot of industrial users of WASM-FX care a lot about. It can be almost full as some syntactic sugar, suspending and immediately resuming something else. I want to mention that we have implemented that instruction in our programming language, but it makes a lot, in our program logic, but it makes the logic a lot more complicated, so I'm not going to be mentioning it anymore in this presentation, just for simplicity. So we'll just focus on the first three instructions, new, continuation, resume, and suspend. And to understand how these work, let's just have a look at a simple example in WASM-FX. I've got two functions here. On the left, I've got my auxiliary function. If you've never seen WebAssembly code, it's written like this as a list of instructions, and you can think of it as a stack-based language. I'm putting one onto the stack, and if you ignore the suspend for one, for now, I'm then putting a second constant 2 onto the stack and then adding them. So this function is basically just doing 1, 2, and then adding those 2 into 3. But as you can see, I've got a suspension here, suspended to the tag T. That's just how I differentiate different kinds of effects that can be introduced. In all of my examples, I'm only using one effect for simplicity, but that's kind of like when you define your new exceptions, you could have many different names here. And to understand exactly what the suspension does, we need to see the code that is actually going to invoke the auxiliary function. That's my main function here on the right. Again, if you've never seen WebAssembly code before, this might look a bit convoluted, but it's organized in blocks like this. I'm just going to enter these blocks. I'm entering block 1, block 2. I'm creating a new continuation from this auxiliary function aux and resuming it immediately. So now I'm running this code. But then when I see this suspension, a bit like when I'm throwing an exception, I will come back to this resume instruction and see if my effect is being handled. And it is here. I have an instruction here that says on T, exit block 2. If I hadn't seen a suspend, then I would have just executed the next instruction here, which is unreachable. So I better see a suspension. But I do see a suspension. It's right here, and it's handled here on T, exit block 2. So I'm going to exit this light blue block, and I find myself in this instruction. At that point, the continuation that I was running and that I have suspended is on the stack. So if I have this resume here, what I'm resuming now is what I was just running earlier. So now I'm going back into my function and resuming the execution. As you can see, I'm saying on T exit block 1, meaning if I see another suspension, I will now be exiting block 1, this yellow block. And then I will see this unreachable instruction. So I better not see another suspension, but all is well because I'm just seeing 2, add, and then this function terminates, and I execute what happens after the resume, which is a return. So this is a very convoluted way of just computing 1 plus 2, which is 3. If I want a slightly more complicated example, I can imagine that my tag is now given a slightly more complicated type, int to int. And what this will mean is that I will carry a payload when I perform my effect. So again, my main function is going to create a new continuation corresponding to my auxiliary function, resume it, so I start running it. I put 1 on the stack, I suspend, and this time, when I suspend, I'm carrying that 1 over to my main function. Kind of like when I have an exception, I can sometimes have arguments to that exception. This tag, or this effect, has a tag type that indicates that I am carrying values over. And so now, when I do on T block 2, I'm exiting this block, what I've got on my stack is not only the continuation I just suspended, but also the payload. That's the value 1. So if I try to call the function f on it and then resume, now when I come back, I've got f of 1 and 2. So now this is a very convoluted way of computing f of 1 plus 2 instead of 1 plus 2. If you're wondering what a realistic program might look like, we could imagine something like this, where the auxiliary function is a loop, where it just does some operation a number of times, and after it's done every operation, it suspends. Now in my main function, if I create this continuation corresponding to the auxiliary function and place it in a local variable k, now I can do a loop where I would resume what is in k. So originally it's this loop function. And then every time I do this sum operation, I would exit block 1 and I will do something else. If I replace the continuation I had on the stack into this value k, I can then repeat this loop. And what I'm doing here is simply interleaving do sum operation and do something else. Now the trick when you're trying to reason about code like this is how do you give this auxiliary function a modular specification? We could imagine that these two are in different modules and we'd like to be able to reason about them separately. But in order to understand what happens with aux, when you see this suspension, you really need to know what is happening in the function that is going to call you, or at least that's the case in traditional separation logic. The way you solve this, as has been well understood for a couple of years now, is by using a protocol-based logic. We've been using Hazel, a version of Iris that is better adapted to reasoning about effects. Instead of having a weakest precondition like what we have in Iris WASM, we have now an extended weakest precondition. Looks a lot the same, but we've got an extra little thingy here in these angled square brackets. The way you read this is my expression E, my program E, runs safely, does not get stuck. If it terminates on a value V, then my postcondition Q holds a V. So far, that's exactly the same definition as a weakest precondition. But now, if an effect is triggered, that effect has to follow a protocol psi. Now, what does this protocol look like? It can actually be very, very general, but most of the time we're going to use a protocol that looks something like this. This is inspired by session types. It's kind of like an answer, a question-answer kind of dynamic here. The way you read this is when an effect is triggered, you want there to exist an X such that the payload of the effect is V, and you have some property P. And then if you ever resume this effect, for all y, if execution is resumed with value w, then you're guaranteed to have q. Now, to understand this better, let's just have a look at our examples again. In my first example, I'm just computing 1 plus 2. Then I can have a very dumb protocol that just says, I'm giving you nothing, I'm getting nothing back. And then I have 1 plus 2. And I should be able to prove this. Calling the auxiliary function just gives me 1 plus 2. In my second example, now I am actually having a payload carried around. So my protocol would look something like there exists an X, such that what I'm giving you as a payload is X. And then what I'm getting back is f of X. And now I should be able to prove that when I call my auxiliary function, what I get back is f of 1 plus 2. In my realistic program, now it obviously depends on exactly what do some operation and do something else is, but I could imagine I have a protocol something that looks something like there exists an n such that I've done my n first operations, and then I get back some q. It's really going to depend on exactly what you're doing here, and then you should be able to reason about this auxiliary function. If we want to have a look at the slightly more technical part of things, the reasoning rules that we define for suspend and resume, the suspend rule is actually really simple. If I want to suspend with a payload V, I just need to make sure that the payload follows the protocol, which in the most general case is written like this. If I'm in the case where I'm using that session type protocol, it looks like, again, unfolding the definition. There exists an X such that my payload is equal to what is specified by my protocol. I've got the property P specified by my protocol. And if I am given that Q that I should be guaranteed upon returning, then I'm able to establish my post condition. The rule for resume is slightly more intricate. What's happening here is I'm trying to resume a continuation K with payload V. I have to have a continuation resource corresponding to this continuation. I need to know that what is inside my continuation can be run safely. That's this weakest precondition. If this ever terminates, that's the normal termination case of my continuation running, I need to show that the post condition here from this premise will imply what I want here. In real life, this is actually a little bit more complicated. It's not just an implication. Otherwise, you could just remove phi 0 and just use phi everywhere. But this is my normal termination clause. And then I've got an effect clause. What happens if I trigger an effect? The definition for this triple is right underneath here. What I want to show is that I am able to actually branch out of the block that is specified by the clause in my resume, and for that I know that I will be given a continuation resource, and I will be given that this continuation follows my protocol. If I unfold this definition in the case where I'm actually using a session type protocol, what happens here is I know that I will be given a continuation, I will be given an X, I will be given an address K, I will be given that property P specified by my protocol, and I will know that as long as I'm able to provide Q, I am able to run my continuation. If you see this for the very first time, this is very convoluted. It feels like black magic, and it felt like black magic to me for a long time, but it works. It's very beautiful, and in the end, it allows us to prove very interesting properties about what happens in iris-WASM effects. So the contributions that we have provided is a full mechanization of the language together with a proof of type soundness, which was the first for this version of WebAssembly, as well as this full program logic that should help verify libraries or verify your own code when you reason about WebAssembly, when you reason about programs in WebAssembly with effects. If I want to give a more general conclusion, this work shows again that machine check proofs are possible even for industrial sized languages, like we probably already know, but this is yet another example of this being done. We think Iris is an ideal tool to reason about these industrial sized languages, and iris-WASM is ideal in particular when it comes to reasoning about WebAssembly and new versions of WebAssembly. Thank you very much.
Any questions? Could you please go to the slide?
Hi, thanks for the very nice talk. I have a question about the type safety proof. So for most versions of Iris, it has a syntactic type safety proof. For your extension with effect handlers, is it still syntactic? Should I be? Okay, sorry. Is the type safety proof for WebAssembly with effect handlers still syntactic, or did you do a semantic proof using your program logic?
We have a proof for syntactic type safety that does not rely on Iris at all. So these are two almost orthogonal contributions. But once you have the program logic, then you can prove a lot stronger things as well.
Okay, thank you.
We have a proof that does not rely at all on Iris. Iris also has adequacy to a theorem, so everything that is proved in Iris can be extracted to a formulation that does not involve Iris at all. So everything that is shown in our paper does not rely on needing to trust Iris. You need to trust our mechanization, you need to trust the rock proof assistant, but not Iris.
Okay, let's just thank the speaker again.
Both of us?
Can you hear me?
One?
Hello.
Okay, great. So the next talk is about code specify test debug proof presented by Zan Armour and Hiroyuki Katsura.
Thank you. Yeah, I'm Zan. This is Hiro. We'll be talking about code specify test debug proof. And so our motivation is that we want greater assurances about system software written in C. System software because it's heavily relied upon. C because you get limited guarantees. And so how might we do that? One approach is to use formal verification, where the user writes rich functional specifications. These are in the form of precondition, postcondition pairs. And the properties we care about are memory safety and functional correctness. And so one issue that's historically been the case is that this is typically all or nothing. So there's a large period of time where the user is iterating on the specifications where they don't get much assurance. And then once the proofs start to go through, they start getting that increased assurance. Another issue is that this is an inefficient feedback loop. And so the user writes the specification, they run the verifier. If there's a failure, they then debug that proof failure. But the simple question, are my specifications correct, is like hard to answer because failures may be due to missing annotations, not just an incorrect specification, and so such as loop invariance. And so we propose an incremental workflow, which is going to build upon the standard code test debug cycle. We're going to focus on specification writing and testing, and this allows us to combine testing and proof in a single framework. And so this is the titular code specify test debug proof. And so focusing specifically on the specify test debug portion, the user will write specifications, but rather than running the verifier, they will run testing. They will look at the testing failure and then see if there's a bug, refine their specifications. And so considering the question that we had looked at previously, are my specifications correct? In this case, you get incremental assurance as more tests pass and classical measures like coverage increase. And then if there is a failure, then that failure will in fact be due to a discrepancy between the specification and implementation. So the full workflow looks like this, where the user is going to write a specification, they're going to perform testing, they're going to iterate on the test failures. Once all the tests pass, they will then move on to proof, and they will then debug that failure and then potentially get a complete proof. And so our graph becomes a lot more gradual, where we start off with unit and system testing, where we're going to instrument existing tests to check the specifications at runtime. We're going to apply random testing. We're going to take the precondition, generate random inputs based off of it to exercise that instrumentation. And then we'll get the full proof at the very end for the maximal assurance. And so one option for choosing a toolchain would be Frama-C. It does support runtime checking of specifications. However, it uses first-order logic, and we want to capture quite complex memory ownership patterns. And so we will look at the CN toolchain, which uses a restricted fragment of separation logic. This allows us to reason about these ownership patterns. And this fragment's already been shown to be good for runtime checking of specifications, random input generation, and formal verification, which were the 3 points on our graph. And so we had to do a bunch of technical contributions to get this working. And so one of those is various improvements to the instrumentation. This include adding support for a bunch of CN and C features, as well as improving performance, both in terms of memory usage and speed. It also involved the implementation of a new random testing tool, which uses an SMT solver, so it can handle quite complex pointer arithmetic constraints. We also added support for ghost arguments, improve the verification speed, and we also did do a lot of engineering to make sure that this instrumentation worked in a bare metal environment. And so why a bare metal environment? Well, we had a case study, which is the PKVM HIP allocator. And so PKVM is a real-world hypervisor for Android developed by Google. It enforces memory isolation between the kernel and guest VMs, the main thing being that it handles sensitive data. It runs in a bare metal environment, so there's no C standard library, limited stack size. And so this really limits how it adds a lot of complexity to what the instrumentation has to be able to do in order to have like full system testing. And so we specifically looked at the HIP allocator, which is an allocator that supports malloc and free. And so how it manages memory is it uses a doubly linked list of these chunks. So here we see 3 chunks, has a header, some data, red used, and then green means that it's free. And so if the user asks for an allocation, potentially we assign that last chunk and return it back to the caller. And so we want to somehow track this ownership. And so we'll consider specifically an internal function, chunk install. And so it's going to take existing, which is going to be a pointer to an existing chunk that's free. It's going to take desired. This is a pointer inside of existing's buffer. And then it's going to split off a portion of that buffer to give us a new chunk at desired. And so a possible precondition, though perhaps this is too weak, wink, wink, is that we just want ownership that existing points to some chunk. We then, after running chunk install, have this new desired chunk. And so one thing that we want to say is that the chunk that existing points to, which is now different, C1, is disjoint from desired. And this, we get this via separating conjunction, so from our separation logic. And so now Hiro will walk through how we can iterate on this specification.
Hi, can you switch this? It's working? Okay, sure, I'm Hiro. And then now, like we've got initial specification for CN, like a chunk install. Then what we want to do here is to like sort of, I will show you how our workflow works for the actual chunk install example. Especially the key point here is that like a gradual assurance. So first we try to use specification as instrumentation and then try to test the implementation by using some unit test cases. Then if you want to get the higher assurance, then we try to apply random testing and then finally prove the correctness, this gradual assurance. So the first step is going to be to use the CN specification as runtime checking. This means that like our machinery automatically converts CN separation logic specification into C runtime checks and then attach these checks with the original program. Then we run the instrumented code with unit test cases. This allows you to track the ownership state and specification constraints at runtime. And especially for the previous initial specification for chunk install, if you run the implementation, then the implementation accesses the memory that the specification doesn't own. Then it will show some error like this. Especially, in this case, it's going to be an ownership error. And then the error message show you like what was wrong with the with the specification. Especially in this case, this address seems to be suspicious. Okay. Then the next step is going to be debugging the specification. Especially our transformation gives you some instrumentation in the C program. You can actually utilize the conventional debuggers such as GDB or LLDB to understand the situation and inspect the program. This is particularly useful because we can print the abstract ownership state in addition to some concrete pointer values or backtraces. Especially in this case, we can show some backtrace of a function, and then you can finally find out, okay, the next pointer of this function seems to be suspicious because this pointer is close to the pointer that you saw in the previous slide. And then probably after some debugging session, you will find out the root cause of the specification. Especially in this case, actually chunk install updates the back pointer of the next chunk. So in that sense, we have to precisely handle the behavior. Okay, it's working. Okay, sorry. It's in order to capture the behavior. I mean, you have to state the ownership of the next chunk in addition to the current chunk. So in that sense, in order to fix this situation, we have to add this ownership statement in the precondition. This is how spec test debug cycle works for chunk install, and then you can refine the specification further and further by applying this cycle. Furthermore, so far we have been using some unit test cases, but actually our specification instrumentation works in the hypervisor itself. This means that we can replace the heap allocator itself with the instrumented version of heap allocator and then run the PKVM itself. This is very useful because we can sort of test your specification and implementation in the actual environment, so you can see how the function is used or what kind of values are passed as arguments. And then especially this is difficult because PKVM is running in a very extreme environment. So you have to deal with some bare metal environment, so you cannot use some C standard libraries, like third-party libraries, or you cannot use some fancy printf functions or such kind of. Also, you have to deal with some very huge code because in the actual Linux build environment, if you apply preprocessed because of the macro expansion, your hyperrocketa is going to be like more than 130,000 lines of code or such kind of. And then our instrumentation machinery needs to deal with this code. And then the fact that our machinery is actually running inside in the hypervisor means that like, our machinery is practical enough to be used. Then, so far we have been using some concrete test cases and then we run the instrumentation code. But if you want to get the higher assurance, probably you might want to get more test coverage. And then for this case, you can utilize random testing. Because CN specification is a per function specification, sort of the high-level idea is that you can generate the test cases from the specifications and then test the situation by using the instrumented binary. And more precisely, we are on top of a separation logic. So from the separation logic specification, our machinery automatically generates the heap structures, and then we try to test the heap structure by using the instrumented code. For this case, we have a fixed specification for chunk install, right? And then from this specification, we can generate heap like this or like that. After you generate the heap structures, you can actually run the instrumented code, and then you will see, okay, this heap is fine, but this is not. And then after some debugging session, you will notice that, okay, desired pointer should be inside in the existing chunk. And then you will notice that, okay, you have to say in the precondition, desired pointer should be inside the existing chunk. Especially, we have implemented a new SMT-based testing generation program, and then this works very well with the edge cases related to some pointer arithmetics and complex constraints on pointers. Okay, after several iterations of these kind of spec test debug cycles, finally you will reach the saturation point where no testing machinery will complain about the implementation and your specification. And then now, at this point, we are ready to prove the correctness of the implementation. And the advantage of our framework is that we can use the same CN specification even for proof. This means that we don't have to switch to a new machinery, and then you can just use the same specification by adding some proof annotation and lemmas. Then finally you can prove the correctness of the implementation. So you can prove that the implementation actually satisfies the specification that you have developed by using testing machineries. Okay? Then maybe you can prove the correctness of chunk install now. This is how our workflow works for the chunk install example, but actually in this work, we have applied this entire framework to the entire PKVM heap allocator. And in this campaign, we have started with some sort of partial specifications for top-level functions, and then refined the specifications by using some testing machinery. And then testing machinery gave us some earlier feedbacks about the specification bugs, and then actually we could find 20 specification bugs during the campaign. Furthermore, we could find some 4 implementation bugs of the PKVM, and then all of which have been fixed by the Google developer already. And then in the end, we have verified the correctness of heap alloc and heap free retroactively, mostly without changing the C code. And this is what we have achieved by using the workflow. And then actually this can be achieved, and then in order to achieve this workflow, we have implemented a lot of things, and also we have developed some theoretical foundation for the workflow. But we don't have much time to talk about all the things, so if you are interested in this work, please read our paper. So let me conclude the talk. So we have proposed code-specified test debug proof cycle on top of CN separation logic. And this workflow itself is very practical in a sense that it works on real-world C code, and also the testing machinery actually runs in place in the hypervisor. And also we found that it was very useful in a sense that we could find many specification bugs without requiring us to actually try to prove something. Furthermore, everything is unified in the single CN specifications language, so we don't have to use a different machinery to prove something, and we can seamlessly prove the things that we have developed by using testing machinery. Now everything is public online, like you can download the CN machinery from the repository, so if you're interested in, please download our machinery and use it. Thank you.
Any questions?
Hello. So I like to talk, and I'm curious. I don't know much about CN, but I assume that it's like specification, like it's like syntactically similar to C, right? Or yeah. Could you tell me more about that?
It's closer to perhaps some like mix of Rust kind of. So like it has ADTs, for example, and so like for like a linked list, one would be like comparing the heap structure of a linked list, like traversing it, and then comparing it to an ADT list. And so then ideally your functional correctness is in terms of like a functional implementation.
So were the specs like handwritten or were they automated? So and were you testing these automated lifted specs?
So here wrote the specification. So the specifications are written by hand. And then the instrumentation, testing, and verification is all like running a command, and it happens automatically.
So could you be able to automate the specification making from the C code?
Well, so we've tried like quite a few experiments of like getting an LLM to do this, and it seems like it works surprisingly well, but
but that is not included in this talk.
That's not part of it.
Okay, thank you.
Okay, then let's thank the speakers again.
Yeah.
Okay, the final talk of the session is about Theresia, presented by Denis Carnier.
Okay, hi everyone. So thank you all for being here. I'll be presenting Theresia. You may be wondering what these words mean, like attestation and capability machines. So let me just motivate this using a running example. So you're to imagine a client process that's running on a particular machine, think of a CPU, and at some point it gains sentience and dares to ask a very difficult question, right? Douglas Adams worded this beautifully. What is the answer to the ultimate question of life, the universe, and everything? And so like any good piece of software, what it does is it's delegating or outsourcing the computation to a lesser privileged component running somewhere else on this machine. The component here is called dplot. This is analogous from the book. Maybe you've read it, maybe you've not. But what it does is it runs this computation for a couple million years and finally returns an answer. Unfortunately, the answer is bogus. So why did that happen? Well, inadvertently, when we outsourced the computation, we compromised the integrity of the results because an adversary was really in control of the kind of software that was running on top of the machine. And so what the client really needs from the, is there a microphone problem? Oh no. What the client needs from the machine is a way to carve out sort of specific, from the adversary controlled memory region, an area of memory that is in some way impenetrable. You can call this an enclave. I'll draw a castle around this memory region to signify that it's impenetrable. And importantly for us, this happens sort of on the fly. Really, we're revoking memory from the adversary and giving exclusive access to this enclave component. The hardware security people refer to this as late launch or a dynamic root of trust. And so this solves our problem because now this enclave basically gets a specific cryptographic key with which it can sign answers. And on the other side of our example, the client can sort of verify who owns this key that signed this answer that I got, and the machine will say, well, it belongs to deep thought. Now, importantly in this story, the signature, or the key behind the signature, it must be linked to the identity of deep thought. In particular, here we will mean that it comprises a hash of its source code. There's some other things which I'm omitting just for brevity. So let's make this more concrete. You guys love code, so I'll instantiate the client and say that we invoke the adversary, we'll jump to it and ask this very difficult question, and then we'll eventually store the result in this res variable. On the other side, the adversary, what it does is it sort of registers this deep thought enclave by calling this init primitive, which sort of revokes some memory somewhere in the adversary region, and it will store the result in this enclave variable, and you can think of this as a kind of closure, which it then invokes, or maybe a function pointer which it invokes. And finally, once this closure finishes, the result is returned to the client. So deep thought itself is a very complicated process, right? So it thinks for a couple million years and then finally returns 42. But of course, we now know that we have this fancy feature, this primitive on the machine that lets us generate a sort of globally unique signing key using this genattest key primitive. And then, of course, we mustn't forget to use that key to actually sign the result. So coming back to the client now, we can unpack this into both the answer and the key. And then importantly, we need to check that the key actually belongs to deep thought, right? Otherwise, an adversary could have picked a different key to sign the result with. And so the way we'll do this on the client side is we know, of course, what the source code of deep thought is, so we can sort of hash its source code to obtain a static identity, and then confirm by calling this a test primitive that the machine has really registered with that specific enclave, that specific key. If that's not the case, we'll abort. And then finally, we'll be able to verify that really the answer that we got is equal to 42. Now, the problem statement is how can I, as a proof engineer, verify the safety of this example? So in other words, provided that the machine did not actually crash, how can I prove that the assert can't fail? This is not that trivial. In particular, we're jumping to and from an arbitrary adversary. This adversary is somehow revoking access to its own memory region to set up the secure region. And then there's this attest primitive that somehow allows us to interact with the machine to infer the identity. And then all this to somehow conclude that there's this property that holds for the answer that we got back. So how do we reason about this? I'm going to come back to the zoomed out example once more. Let's break it down into manageable chunks. So the client code is really known code. We can apply standard Hoare logic or Hoare-style program logic to verify it. The only exception is really the interaction with the adversary, and for this we basically define a logical relation that captures this intuitive notion of what the adversary can do, sort of giving an over-approximation of all the things that it could deal with, or what the worst thing is that it's capable of doing. But then finally the difficult part is the enclave itself. So how do we verify this? And this is really the key challenge and what I intend to devote what time I have left here. So it's the solution that we came up with is basically three ideas. So the first is we need a way to reason about memory revocation. We need to ensure that we have exclusive ownership, or that the enclave has exclusive ownership over its own memory region. Second, we need a way to deal with cryptographic signatures, right? We need some way of reasoning that sort of signatures mean something for specific signed values. And finally, there's this attestation problem, which is the client has this specific signature and it wants to know who does this key belong to, and the machine says, oh, that key, that's for deep thought itself and nobody else. These first two ideas were basically reusing techniques from the literature that we adapted, and the third one is really the most novel part of the paper, I would say. So the first part, so reasoning about memory revocation. Earlier I drew these kind of arrows to mean that the adversary had some way of still getting into this deep thought enclave, and we need a way of getting rid of these arrows. So in order to explain this, I need to kind of lift the veil a little bit on the underlying machine semantics that we're dealing with. So very operationally, we're dealing with something called cherry tree, which is which was published at EuroSMP in 2023. It's a kind of ISA extension implemented on top of a Cherry RISC-V processor. Cherry RISC-V is, of course, this capability hardware-enhanced RISC instruction set. And for those of you unfamiliar with capability machines, on this style of architecture, sort of traditional memory pointers, they're replaced by something called memory capabilities. And what this means is you can think of it as a for tuple. There's some permissions that you get with this memory capability. In this case, it would be something like read, write, and then there's various bounds. So there's a B for a begin address and an E for an end address, and then of course the pointer address itself, A. And then the machine will actually dynamically check these bounds during execution to ensure that the pointer is really pointing inside this region and that you have the right permissions to do what you want to do. In case you want to dereference the memory, you need a read permission, etc. But so Cherry Tree specifically extends Cherry with sort of a minimal set of extra features to, on top of this sort of memory isolation idea of Cherry, support this enclave model that I've been sketching before. And so what it does is it adds something called sealing and sealed capabilities. They essentially allow to sort of close over memory capabilities, and they model a kind of symbolic crypto. And then, by the way, this is not a new contribution for Cherry Tree in particular. Sealing capabilities already existed. But also we need a memory sweep mechanism. When the revocation happened earlier, we need a way to be able to go over all of memory and all of the register file to ensure that nobody still has capabilities that point into the region that we want to reserve. And then there's some extra special purpose machine state to keep track of which enclaves have registered and in order to hand out sort of fresh keys. So for this last part, maybe I can go back to the example from before. So when the adversary initializes this enclave and the enclave calls this genAttest key primitive, there's a kind of table that keeps track of enclaves that registered that specific key with that specific enclave. And then on the other side of the story, when the client actually gets that result back and it calls this a test primitive, it's sort of verifying that that key really belongs to the enclave it's interested in. And so reasoning about this is kind of analogous. This is what we realize. It's analogous to kind of stop the world garbage collection, where you have a bunch of GC routes and you're kind of traversing and sort of freeing up memory. And Gil Her, I think is his name, or pronounce it his name, together with Derek Dreyer, have already come up with a program logic to deal with this. So sort of roughly what they do is they have memory addresses which they now index with a logical version, and when sort of the stop the world garbage collection happens, the specific logical versions are bumped to hand out new points to chunks. So we borrowed this for our capabilities. And then secondly, for cryptographic signatures, there's this seminal paper by Sumi and Pierce that associates logical predicates with signing keys, and this is precisely the kind of thing that we needed here for our symbolic crypto. Roughly, because the keys cannot be forged, so we can sort of conclude that all values signed by a specific key have a sort of logical predicate that we can associate with them. And then the final sort of ingredient in the mix is this attestation reasoning machinery. And for this, we came up with sort of three key elements that we kind of combine to be able to do this end-to-end proof. In particular, the first part is this custom enclave map. So we have a logical map. And what it does is it kind of associates with a static identity for a particular enclave logical predicates. And then we also register a system invariant that sort of keeps consistency between the machine state and its logical state. In particular, on the left, you have this key, which is very operational. It's a specific key that was assigned by the machine for an enclave. And the machine keeps track of this using this E table with the identity of the enclave. In turn, the custom map couples this identity with a logical predicate, and all the while we use this idea from Sumi and Pierce to tie the key to this predicate as well. And then the third ingredient we need is a custom enclave contract. Basically, we need to ensure as the proof engineer that our enclave is really only signing what we know are sort of good values, or values that respect the signing predicate. And it's also important that we verify that we're not actually leaking our key, because otherwise the adversary could sign arbitrary values with our key. So how does it apply to our example? I'll maybe come back one last time. So the custom enclave map, we can sort of instantiate it as having a single element that maps to DT, that's short for deep thought, a logical predicate that says any word signed will be 42. And then the contract for deep thought itself is you're only allowed to sign values that are equal to 42, and you never leak your key. And for the no code, we can use a system invariant. And so to sketch the proof, initially on the top right, we have this custom enclave map. And then we use this program logic to verify the client code. We model the interaction using the logical relation from earlier. And then the enclave proves its enclave contract, ensuring that it only signs 42. And now our invariant is actually holding, like keeping this all consistent. And so when this client receives this message from the enclave, it can actually use the invariant to determine that the value will be 42, completing the proof. I believe this sort of relatively intuitively captures sort of what you want to expect in the proof. If you're not satisfied by this example, the paper has a bunch more stuff. So we do things like mutual attestation, where you have two enclaves that are mutually distrusting of each other, and inside the adversary they have to establish trust. This induces a circularity because essentially one enclave requires knowing the identity of the other enclave and vice versa. So we need a way to break this. And there's also another case study on a trusted sensor which roughly models MMIO. We don't actually have MMIO in the machine model, but it basically is a stateful example. And there's a second enclave that then processes this sensor's data so that we can conclude things about it. So to conclude the talk, we basically did this, we designed this program logic for attestation. We are able to establish end-to-end theorems for these examples that involve both known and attested code. And if you want, there's more complex case studies in the paper. Finally, everything is also verified in Iris in about 35,000 lines of code mechanized inside of ROC. And with that, I want to thank you for your attention. I'll be happy to take any questions you have.
Questions?
Yeah.
So I haven't understood yet the motivation for introducing the enclave-specific key. It would seem like instead you could have an abstraction where there's some kind of communication channel between the enclave and the client code, and the communication primitive returns the ID instead of the key. Where you have tuple AK, you get the tuple AID instead, and then you've saved some steps of processing. What do we lose if we do it that way?
So the key in particular is needed because we cross the sort of untrusted boundary. We have no secure channel, essentially. That's the thing we're missing. So the key is really allowing us to cross this adversary. Like we have this adversarial boundary between where the enclave lives and where it wants to communicate with the client, and we have no sort of secure channel. The key is a sort of way to establish a secure channel.
There's some other more global key involved in the attestation mechanism?
So the key is global. So the attestation key that the enclave gets is global with respect to the machine. It's unique.
Got it. Okay, I might have to bug you about this offline.
Okay,
Thanks.
that sounds great. Looking forward to it.
Any other questions?
Yeah. Sorry, can you speak up a bit?
Can you speak with the mic? Sorry.
There's one over
there.
here.
Is it on? Yeah. What about the crypto primitives themselves? What do you do about that? Is that also verified?
So it's a symbolic crypto. So.
But you can execute the system, right?
Yes.
And what concrete crypto do you use?
It's a symbolic crypto in the sense that so the machine has capabilities on it. There's kind of these abstract objects, and there's kind of an operation to sort of seal these capabilities. So there's no actual like 256-bit encryption key that exists. It's kind of just a tag bit on the capability.
Oh, so the signing is not really a cryptographic signature?
Yeah, no, exactly. Yeah, so it's kind of a machine primitive to encapsulate a memory capability.
That makes more sense. Yeah,
Thank you. Yeah.
We still have time. Other questions?
Maybe we can grab an early lunch.
Okay, let's thank the speaker again.
Thank you.
We'll be starting in about 30 seconds. So if you have friends that are still out there that need to get in here, make them run. If you are from Yale University, or you know that you have a talk in this session and you have not yet AV checked, please come and find me. All right, let me introduce the session while everyone's filing in. Hi everyone, welcoming to the Networking and Distributed session. This is our first after lunch session of PLDI. Get excited. I'm May Milano, I'll be your session chair. We'll be doing 17-minute talks, 3 minutes for questions. As always, please hold questions until the end. If you have to AV check for this session and you have not AV checked yet, raise your hand. Seems like no. Then let's go ahead and get things started. Anchi, are you connected up? Can you try again to get connected up? Hi friends, I'm really loud. Can we turn me down? Thank you. Louder? I'll moderate. Oh, now it's off. All right. I'll moderate my own volume. I'll shout into the mic or whatnot. It's very fun to have the like twiddling on the side though. So we are rebooting this first speaker's computer because of a minor technical difficulty, which means I get to do my favorite thing at any PLDI, stand-up comedy. How are we all doing today? Right, I see a lot of fun faces in the audience, people I recognize. Like, for example, I see our second speaker. In about a minute or two, if this isn't working, I think it might make sense for us to switch the schedule order just so that we can get started okay. That doesn't seem very happy to you. Is there something we could do to make that possible? Ishel's in the room. Well, Ishel was in the room. Okay, great. There you are. Great, we'll give it another minute or so. At the same time, though, I don't have an extra session to put a spare talk in. We can see the screen. We can see the screen. This is so exciting. So for this session, we are going to have to reduce our question time to about 2 minutes per talk, just to be able to stay a little bit closer to on time. I'm sorry about that, Anchi. But thank you all. I hope you appreciated my definitely stand-up comedy routine. And we'll get started with our first talk. This is Anchi from the University of Utah, talking to us about, I assume, cache coherence.
Okay, right. So modern chips combine multiple processors to run workloads efficiently. So for example, the NVIDIA Grace Hopper chip uses a CPU and GPU with shared memory between them. So each device's coherence protocol is glued to the others through this global coherent interconnect, so like CXL, CHI, NVLink C2C, and in Grace Hopper it is NVLink C2C, and that gluing is what lets the two devices share memory. So when the CPU-GPU program is compiled for such a chip, the CPU and GPU code are typically compiled independently, each with their own mature compiler, and all the communication between the two devices goes through shared memory, supported by hardware protocols. And independent compilation relies on these protocols composing directly. Now, to see what this shared memory communication looks like, consider a simple CPU-GPU litmus test. So initially, all values are 0, and the CPU writes a 1 to a data object, and then next in the preserved program order, sets a flag to signal that the data is ready. And here, preserved program order means that the CPU memory model guarantees the writes are not reordered. And then on the GPU side, the GPU reads the flag within acquire, and if the flag is set, reads the data. So the expectation is that the GPU sees the new value and not the stale 0. So, and because these two sides are compiled independently, this only works if the CPU's ordering rules play well with the GPUs. Now, if the hardware has glued to the two sides correctly, then the GPU's acquire reads from the external CPU and from the flag, and then observes that it's set. And once that flag is observed set, the ordered data read after it must read from the external CPU right to the data. So it cannot observe a stale value of 0. So all of this hinges on one thing, that the hardware correctly glues the CPU and GPU together so that the device's preserved program order is preserved in the fused system. The notion of the heterogeneous correctness in this system was recently formalized as the compound memory model. And in short, today's practice of independent compilation rests on the CPU and GPU playing well together. And that playing well together is what exactly compound memory consistency is. So achieving compound consistency is tricky. The hardware has to be carefully designed to enforce it, and getting it right is subtle even on commercial silicon. So if we take the Apple M1 as an example, it supports 2 memory model modes, 1, a TSO mode, and 2, an ARM mode, and each of its preserved program orders and communication relations are of TSO and ARM. So when we run the same litmus test with one thread in TSO mode and the other in ARM mode, each thread independently obeys its own model, but the composition does not respect the ARM TSO model, and the litmus test is violated. But in the single modes where it's just TSO and ARM, they are not violated. But here, in this mixed mode, the data legally can read a stale value of 0, even when the acquire reads a 1 for that freshly set flag. So this forbidden cycle is allowed. And we have conveyed this result to Apple, and we are not claiming it's a bug. TSO mode is an undocumented feature intended for x86 emulation, and Apple has confirmed it is not meant for cross-mode shared memory synchronization. The point is simply that achieving correctness in a heterogeneous setting is difficult. So ideally, these compilers and programs for these chips should just work unchanged. So in other words, we want the system to satisfy the compound memory consistency model, the CMCM. And to achieve the compound memory model, designers have to apply this de facto standard. They add these translation shims between each processor's coherence protocol and a global interconnect. And when a memory operation propagates within a cluster, the shim intercepts it and synchronously propagates it to the other devices as well. And this synchronous propagation rule is used extensively in academic designs and appears to be used in industry as well. The question is it correct? And in this work, we show that it is. Synchronous propagation already correctly enforces the compound memory consistency model, and the result is general. It applies to a broad class of CPU and GPU style protocols in use today. So specifically, as long as the individual CPU and GPU protocols satisfy the properties we describe and prescribe, the global interconnect satisfies the single writer multiple reader invariant, SWMR, enforced by protocols such as CXL and CHI. Then synchronous propagation guarantees this compound memory model. And this work therefore provides this formal foundation for heterogeneous shared memory today. Furthermore, the result enables a composition approach to verification. Designers only need to verify each individual protocol against the properties that we mandate and check that the global protocol satisfies SWMR. Our compositional proof, 26,000 lines of lean, then does the heavy lifting and shows that the composed system enforces the compound memory model. So there's a huge variety of coherence protocols across CPUs, GPUs, and other accelerators. And our theorem has to hold for them all of them. So the hard part is that CPU and GPU protocols are fundamentally different. In CPU protocols, a writer eagerly invalidates the other sharer's copies. And in GPU protocols, it deliberately avoids this writer initiated invalidation. And instead, it can cache or write back data, and upon a release, then write back, and it will self-invalidate other caches upon inquire. And a moment ago, we said that our result holds for any protocol satisfying these properties that we prescribe. But how can one set of properties span protocols that's different? That is a central challenge. So how do we reason uniformly about this plethora of protocols? So let's understand how these protocols work using the same message passing example. So here we have two CPU cores, each with their own cache, holding both data and flag in the shared state with initial value 0. And when the core 1 writes the data, it sends this invalidation that removes core's 2 copy of the data. And then when it writes the flag, it likewise invalidates core 2's copy of flag. And then later, when core 2 reads from the flag, it misses in its local cache and fetches the up-to-date value, and the same for data. So this is SWMR, this writer-initiated invalidation behavior. A write will eagerly invalidate the other sharers, so stale copies cannot linger. The GPU, however, as we'll see next, takes a very different approach to coherence. So in contrast, a GPU protocol works very differently. So consider two CPU cores, both caching flag and data locally with value 0. When core 1 writes to data, it will simply update its local cache. It does not need to send any invalidation to core 2. So at this instant, core 2 still holds its local stale value of 0. And then when core 1 does a release on the flag, it will write back that dirty data to the shared LLC, and then it'll write back its flag to the LLC. And then when core 2 reads from the flag with an acquire, it'll bypass its cache, grab that fresh value from the LLC, and then self-invalidate its local cache. So then its subsequent access for the read will miss and then fetch the new data from the LLC. Right. Now, consider a combined CPU and GPU system. The key players are the shims that connect the CPU protocol and GPU protocol to the global protocol. And again, assume that the flag and data are cached both locally in the CPU and GPU with values of 0. So when the CPU writes data value 1, then it sends this request to the directory, and the shim will then intercept the message and then synchronously propagate it into the global protocol as a global invalidation, and then and then the local write does not complete until that global step does. So the global invalidation needs to reach the GPU and validate the copy of the data in the GPU's LLC, but not change its local cache. And the write of flag to 1 does the same thing, invalidating the GPU's copy of the LLC of flag. Now, when the GPU performs an acquire, it bypasses and self-invalidates its local cache and goes to the LLC. The shim intercepts that miss and synchronously issues a global coherence request, which causes a flag held in CPU's 1 cache to be forwarded. And then the subsequent read value of the data likewise misses and is forwarded to the CPU. So how do we reason about the correctness of all of this? And in particular, how does it satisfy compound coherence and consistencies? Yeah. So our key idea is this unifying abstraction for coherence protocols, one in which we can express all of these very different protocols. And the abstraction has to walk a thin line, be rich enough to express every protocol, yet abstract enough that we can reason about correctness uniformly across all of them. So to that end, we present 3 ideas. So first, linearization points. This is the point at which a coherence protocol makes a memory operation visible. And as we'll see, we distinguish between local and global visibility. Second, abstract states. This is a uniform way to capture a cache holding sufficient permissions to satisfy an operation locally as a silent hit without further communication, whether it's a GPU or CPU cache. And finally, consistency labels. Each operation carries a label, its ordering contract, which is how we relate behavior of the coherence protocol to the consistency model it must enforce. So let's see these 3 ideas in action and go back to the litmus test we explored. So considering the CPU writing data, it misses and is sent to the cluster directory. And at that point, that's where the shim intercepts it and the synchronous propagation rule propagates it to the global protocol. And here in this global step, this is specifically synchronous. So this global operation is encapsulated by the local request. And so the global linearization has to finish before the local operation completes. And then for two CPU writes, so for something like a data and then flag, both are serialized across the cluster directory in that order. And because each global step is encapsulated within the local requests, the global linearizations occur in the same order. So in other words, when the local linearization occurs, it is carried over to the global order, and that is exactly what preserves the CPU's local order globally. So now for the harder case, where both data and flag are already held in modified state in the CPU's cache. So when we run the same litmus test again, but now with the two writes being silent hits, so they have permissions, no request reaches the cluster directory. So there's nothing for the shim to intercept. So how is this propagated globally? And that's where the abstract states come in. We can mark both blocks as write coherent, and the key point being here that the cache can only reach this write coherent state by having earlier acquired the line through the directory via synchronous propagation, the global protocol. So the cache state is a cached proof that the global linearization has already happened where the line was brought in. So this is where the previous slide's global step happens now, but here in this case it happened earlier. And the abstract state records this fact. And because the global protocol is SWMR, no other cache holds these blocks. So any later read in anywhere on the chip is forwarded on to this cache. And we'll see the correct value. Right. So the final piece is the consistency labels, through which we capture the ordering guarantees the coherence interface provides, effectively attaching an ordering contract to each request. So CPU protocols, for example, carry SC read and SC write labels because they enforce SC at the coherence level. More importantly, or specifically, this is the consistency model at the coherence level, not the architectural one. So any SC enforcing coherence protocol can still realize a weaker architectural model like TSO, ARM, or RISC-V through pipeline reordering. GPU protocols in the same vein carry acquire read and release write labels. And by attaching these labels to coherence requests, we can reason about the consistency effects of a coherence protocol, and that is exactly what connects the coherence to compound consistency that we set out to try to prove and enforce. Right. So is our abstraction just a toy, or can it express realistic protocols? And it can. So on the SWMR side, it can express the MOSI family, so CXL cache protocol, ARM AMBA-CHI, and on the GPU protocol, it can span anything from simple write-through self-invalidating protocols to, in the style of these commercial GPUs, up to advanced ownership-based protocols like de novo from academia. So we're able to model all their behaviors as axioms. And we don't just express them. To make this concrete, we model check these two protocols end-to-end against our axioms, so CXL cache and industrial protocol, and de novo, an advanced academic protocol, and both of them are instances of our abstraction. So we prove that, okay, for any P1, P2, protocol 1, protocol 2 that satisfies our axioms, that satisfies the SWMR properties or RCC properties, they'll compose so long as the global interconnect satisfies SWMR. So then the composed system will satisfy this compound memory model. And this entire proof is on lean and it's available. And what makes it useful in practice is that a designer only has to verify that their individual protocols satisfy our axioms. Our theorem then guarantees that the composition is correct by construction. So in summary, today's heterogeneous shared memory systems, such as Grace Hopper and others, run independently compiled code that rests on an unstated assumption that machine satisfies compound consistency. And how do we get to compound consistency? Here too, the field has relied on an unverified rule, and that is synchronous propagation. In this work, we prove that this rule is correct and machine checked in lean. So our result does two things. It places heterogeneous shared memory on a formal foundation and enables compositional verification of future hardware, where you just have to simply verify that each protocol locally satisfies the axioms, and the composition is then given correct by construction. It took decades for homogeneous machines to get to the formal consistency foundations, and heterogeneous machines don't have to repeat that history. Right, that's it.
While the next speaker is setting up, we'll have time for just about one quick question. Well, I have a quick question then. Sometimes I see heterogeneous clusters that actually don't have globally coherent caches or otherwise have old or unreliable hardware that participate in it. Does your compositionality result extend to those clusters and say something about the residual coherent component of the cluster actually will have guarantees? Or does the presence of non-coherent hardware break everything?
Okay, so specifically if there is no coherence protocol in the device.
I'm saying I have like an old style hybrid supercomputer where I have some non-coherent memory and some coherent memory. The coherent memory has a similar interconnect to what you're describing, but the non-coherent memory also exists. Do your results say anything about the coherent portion of my system, or does the presence of the non-coherent portion invalidate your assumptions?
Okay, so so the proof doesn't directly handle that, but the proof framework does extend to this kind of system. So long as you have some primitives or axioms that you can describe to reason about those non-coherent actions, then you can incorporate them and make them work with the proof framework to show that there's some kind of compositional model with that.
Great. Let's thank the speaker one last time. Next up, we have a distinguished paper talk by Eric Campbell talking about data plane portability. I should also note that Eric, distinguished paper author, is on the market this year. So if you're hiring, take a look. Take it away, Eric.
Can you hear me? Yes. Okay. Thanks, May. Thanks for the plug. And just another fun fact: May and I were roommates at Cornell many years ago. So this is a great. Glad to have you as my chair. Right. So I'm going to tell you about some cool work that I've done with some great students, Robert, Divyanshu, and my postdoc advisors at UT Austin, Aditya and Ishal, about our tool called Matchbox, which is a semantic foundation for data plane portability, which means networking. So network programs, particularly in the data plane, are built around a particular abstraction, the match action table, which in this talk we're going to interpret broadly. This is true for traditional networking, where a control plane, or in the context of software-defined networking, a controller computes a set of routes and then creates a set of tables that, say, a switching ASIC uses to forward packets in the actual network. Match action tables are also fundamental in cloud computing, where user-facing access control policies are compiled into tables, firewalls that are then executed by the cloud environment or in the cloud environment. Or even in the kernel, where something like a CPU load balancer can be compiled to match action tables that then get run by eBPF programs. And as a quick terminological aside, I will often say switch to refer to this execution, but I just mean that, I mean switch as sort of representative terminology. All of these situations are for this talk included within switch. So let's look at what a match action table is by example. Structurally, a match action table is a lookup table that inspects packet fields and then indicates the action that should be executed by the environment. At runtime, tables are populated with rows that first specify bit patterns against which the packet is to be evaluated. And then the corresponding action is to be executed. So this particular notation we're using is a slight bastardization of CIDR notation, where we're showing these 32-bit IPv4 addresses byte by byte, and the star is a wildcard that says the remaining bytes to the right can be anything. And so this first row does not match this packet, because the first 2 bits of the source address are different. The second row does, however, because it first doesn't care about what the source address is. And then the first 2 bytes of the destination address are the same, 10 and 1. And so the match action table has selected the forward action with arguments, named arguments, port is set to 303. And so once an action is selected, okay, anything below that, the remaining rows with lower priority are ignored. But the problematic, and then the selected action is passed to the environment, which executes the action with these arguments. And what's problematic here is that the environment has a pretty free choice with respect to what these semantics actually mean. which can cause problems when you're trying to reason about multiple switches in the same network. So if I want to support two identical seeming switches, this one on the left and this one on the right, these switches are going to interpret the forwarding actions identically. But we're going to start to have trouble with the unknown action. What do we do when we don't know how to forward a packet? And so just for the sake of example, we're going to say that the switch on the left drops packets it doesn't know what to do with, which means the packets fall onto the floor, they're discarded, they cease to exist for the purposes of the talk today. Well, on the right switch, the switch is more curious, and it's going to flood the packet out on all of its ports in a hope that when one of them responds, it can potentially learn what the correct forwarding behavior is. So this is sort of a pattern common in learning switches. But the problem here is that while these match action tables have both the same interface and are literally the same tables, the same data structure, they have completely different meanings, and they do completely different things and serve very different roles in a network. And this variation in environments is not necessarily because one or the other is buggy or wrong, or you've made an engineering poor engineering choice. These are genuinely a result of real engineering choices in which operators and engineers need to optimize for different kinds of workloads. Okay, so we need some way to work with this variation. And that's what Matchbox provides us with. That's what we're going to talk about today. A semantic foundation for manipulating match action tables themselves. We're going to be able to construct new ones from old ones so that we can port them across switches. And in this example, we'll use Matchbox to transform the tables of this unknown to drop switch to the flood switch. Okay, there's an arrow. Let's see how. So say that our semantically varying route tables occur in the context of this second table, a filter table that I'm not going to show you, but either allows or drops a packet based on the same keys as the route table. We need to ensure that this new filter table, filter prime, drops every packet that route floods, right? And the new route table, well, that's just going to be the same because it's the only table that gives us any ability to forward packets at all. So the way that we're going to do this is write a match algebra expression to define the semantics of this filter table. This match algebra expression is maybe complicated at first brush, but is not actually that complicated. The first thing that we're doing is we're taking the so-called parallel join of two tables. And the idea here is that we're going to compute the joint decision that these two tables make on all the packets for which they're defined. And then we're going to transform the actions that are computed, which is a pair of actions because there are two tables. And we're going to compute the metaphorical and of those decisions, which is if the packet is both forwarded and allowed, then we're going to allow the packet. Whereas if it's either dropped, if the route table doesn't know what to do with it or the filter table drops it, then it will be dropped. And so this has the consequence that floods are dropped by the filter table, which is what we wanted. And this makes the switches sort of equivalent when we populate the switch on the right with this program. Okay, so aside from this match algebra, we need a few other things. The first is a type system, because the match algebra expressions, okay, there's a lot of little details about header fields and bit widths and all that stuff, and we can build a type system for that, but that's not all that interesting. It's sort of just turning the crank. But what is more interesting is that the match algebra expressions may not always express literal tables. So many of the operators, in other words, are not closed under match action tables. And so we develop a type system that ensures that these operators are in fact closed under match action tables when they are well typed. And then finally, we have a monadic compiler. Compiler is a bit of a funny word for it, but we just mean that we're going to use the match algebra term to translate a set of tables into the desired set of tables. And unfortunately, to spare you a barrage of notation and monads, I'm going to skip the monadic compiler and focus on the match algebra, its semantics, and the type system. Let's start with the match algebra. It's fairly concise. It starts with some operators for literal tables, capital T, table variables, lowercase t. We're not going to go into those. Those work exactly as you expect. Table refinement, which we'll talk about. Table preference. We're allowed to transform the outputs of tables. We're allowed to manipulate the match conditions of tables. We can do this parallel join that we saw, and we can also compose tables kind of like functions. So let's start with refinement. And specifically, this is domain refinement. And all it does is it says, hey, you have a table. It's actually only going to be defined on this subset of packets. So here I have a table route, and I'm trying to refine it to be defined only on those packets where destination starts with 10. And so if I have a packet that starts with 10, great. It's just the semantics of route. Otherwise, if I have some other packet that doesn't satisfy this, here this one starts with 127 instead of 10, then actually the table doesn't matter. And the behavior is undefined. Because we have undefined behavior, we need some way to compose tables. And we do this with compose tables when they're undefined. And so to this end, we have preferential union, which says, try the thing on the left, sort of the greater than side, which means that it's preferred. Try the thing on the left, and then if that's undefined, do the thing on the right. So here we're going to run this filter table and say, hey, great, this packet is defined 10.1.9.9. We can allow it. Great. If we can't, if the filter table is not defined on a packet, here it's undefined on 127.0.0.1, then we're going to use this literal table, just as an example, that matches on everything and then denies the packet, which is sort of a sensible default behavior for a filter to do in sort of the access control pattern. Okay, so next we saw this earlier, but we can transform output actions and, of course, also their arguments. And to do this, we run a packet through the table just as normal, and then all we do is we execute whatever transformation we've implemented on that action and the arguments. So here we're just saying that if we're going to forward out on port 303, we're going to rewrite that into an action called next, whatever that means. Again, that's for the environment to tell us, and then rename port into hop. And so we get out next hop is 303. Okay, before I move on, we can also refine and modify the domain, the keys, but that's going to cause us a lot of problems. So we'll do that last, even though sort of on the left it's next. Okay, so the next thing is this union that we saw before. Sorry, not this union, this join that we saw before. And to evaluate on a packet, we run the packet through both tables, filter and route. And with the rules that we get out, what we do is we pair them. And this was actually sort of contentious during the design of this system. Everyone had a different idea of what this pairing operator should be. Some of us were like, this should be sequence, this should be parallel composition, this doesn't make sense. Match action tables only have one action, what's going on? And actually, all of these are true, and that's what makes this hard in some sense, is that match action tables can run multiple actions in parallel. They can actually decide to run them in sequence, or they can be restricted to only a single action. And so our approach here is to just be agnostic and say, this is up to the environment to decide how to interpret what a pair of actions means. But as a result, this means that this join operator is not commutative. If we swap filter and route, then the actions themselves are swapped in the output. And okay, if your execution environment, if your switch does have some commutative semantics here, maybe you can maybe you can reorder them, but that's not the case in general. Okay, so next to last, we have sort of function composition, which behaves more or less exactly as you'd expect. You have a packet, you run it, and then you get out just the named argument list, and you sort of pun the next argument list as the next packet. And so that allows you to compose these things in a sensible way. And here, what this example is doing is it's computing a link aggregation group identifier for sets of packets, and then forwarding in the second table grout based on those, based on that group. And what we get out is just the second action. We sort of throw away this first action, which sort of corresponds to the use cases that we found. But you can actually recover the original action using parallel join. OK, so here's where the rubber meets the road. Let's think about transforming the table keys. And now I'm only going to show you the easiest transformation, which is projection, because it gets really hard. It gets even harder when you start thinking about rewriting table keys and all of that. So let's try to just project this table to the destination address. And so morally, this should be easy. We should just take the databases approach and say, OK, we want to remove the source column. Let's just throw away the source column. That works in databases because you have relations, and the data is the relation. But here we have match action tables are really programs. They're not data. And so what happens is we're kind of taking the pre-image of this projection. We need to find some packet that is equivalent to our given packet via projection, and then we run that through the program to get some action. And again, the problem, because this is kind of a pre-image, is that there might be many programs. And so this is what I mean by we're not closed under, like our operations are not closed in match action tables. Okay. A little bit speaking more slowly than I thought I would. So, but this is the point of the type system, right? So the type system is meant to solve this problem. So if we have a table that is a bidirectional firewall, we're going to give it this type that looks at the table keys and says, hey, these keys are sufficient to produce the output. Let's say we have another table that's a firewall that just reads in one direction. It's not bidirectional, maybe because the other direction is deduced. And so to get this ingress table, we sort of throw away that extra information, the rules that correspond to the outgoing traffic, and then we can do our projection. So one thing we could do is sort of track this tableness. But this is not going to work because we're not closed under tables. And we kind of, what ends up happening is we can't actually, if we refine, we still have the same set of keys. And so when we try and do the projection, the type system still thinks that we can have bad behaviors like this. And so we reject this program even though we actually would want to keep it. And so our solution is something called guarded functional dependencies. And this is the core of what our type system is based on. And the idea here is that we add refinements into the type that we can then discharge via implication to then deduce that this is actually a safe implication, a safe transformation to do. And this is what permits our monadic compiler, which is very clean and very concise because of this monad that we identified. OK, we have some case studies that show that this applies in a lot of situations. I'm running out of time, but we did some programmable switch evolution. We came up with a unified interface for a bunch of cloud firewalls, and then we did some sharding in eBPF. And there's evaluation data in the paper that shows that we can support industrial sizes at industrial speeds, so say my collaborators. OK, sorry that was rushed, but thank you.
We do have time for some questions. Please come up to the microphone if you have the ability to do so, and if you do not, please raise your hand so I can find you. While we're doing this, I don't know who the next speaker is, so please.
Great talk and lovely results. Just wondering whether your data planes can support features like tunneling.
Sure.
They can.
Yeah, I mean,
your batch actions. Can your switches talk between layers?
Sure. yeah.
Okay.
We're very agnostic in what the data plane actually does.
Okay.
All we care about is the interface. We're just talking about the match action tables.
Okay.
So whatever sort of advanced features that exist in the switch itself, that's fine. We can still support tables that manipulate those.
We have time for one or two more questions while the next speaker sets up. So please start setting up. I have a question for you. You talked about a really expansive notion of what switches were at the very beginning, and then we saw a really clean and beautiful algebra that captures what you can do with Matchbox. I imagine there's a little bit of daylight between the broad space you tried to capture and what Matchbox itself handles. What don't you handle?
There's a bunch of things, but one thing in particular is, one thing you could do in, say, eBPF with these kinds of tables is compute the number of rules in the table. And when you're taking a semantic perspective where you don't care about the representation of those tables, that question doesn't make sense because at the semantic level, because the size of the semantic relation is all the transformations, right? But that's not what the question that the eBPF programs want to ask. And so in order to support things like that, we do need some kind of perspective shift in the way that we're conceiving of this problem.
That makes a lot of sense. Let's thank the speaker one last time. We're going to have a slight tech delay as we get your laptop plugged in. Can I ask you to plug your laptop in first, just to make sure that works? We're doing a microphone check right now. Please talk to me. Hello? Are we getting anything in the back? Great. Our next speaker of the session will be Long Fei, talking to us about verifying termination in Byzantine protocols. Take it away, Long Fei.
Okay, so I'm Long Fei Chiu from Yale University, and I'm going to present our result on formal verification of asynchronous Byzantine consensus protocols. So let's begin from a review of the concept of consensus protocols. It's one of the central problems in distributed computing. And the goal is to achieve safety and liveness while tolerating a subset of Byzantine faults. And any distributed protocol needs to make some assumption on your communication model. And usually in the literature, we have three kinds of communication model. Synchronous model just means your messages are always delivered within a certain bound. But it's a very strong assumption in practice, so most protocols make a partial synchrony assumption, which means the network can be either synchronous or asynchronous. However, these protocols cannot tolerate, they cannot maintain liveness progress if you have an asynchronous network. And so we have a third class of protocols, which is asynchronous consensus protocols. These protocols do not need to make any assumption on network latency as long as it's eventually delivered. Now, if we look at the literature on these classes of consensus protocols, we see that for partial synchrony protocols, it's considered easy to implement, and its correctness is by now probably very well understood. And we have a very long list of works verifying the correctness of these protocols. But if we look at asynchronous protocols, we see a very different picture. They are considered very notoriously hard to understand, difficult to implement, and we have very few results verifying their correctness. So why is asynchronous consensus considered much harder? Well, first, there is a well-known theorem called the FLP impossibility theorem, which basically says you don't have deterministic liveness or in the asynchrony world. And so every asynchronous protocol needs to make some probabilistic decisions in order to make progress. And probabilistic programs, especially probabilistic distributed algorithms, are very hard to implement because you can have a very subtle bugs. And also here, you don't have your deterministic liveness guarantee. What we actually have is probabilistic liveness. Your command will be executed with a probability that converges to 1 over time. And we call this almost sure termination. And the other factor is that if you look at the design of these protocols, you see they have much greater structural complexity. If you look at the protocols like Raft or even Jotion, these partial synchronous protocols, they are easy to describe. But with asynchronous protocols, you usually have a large bunch of cryptographic components. And in fact, there is a well-known bug concerning a protocol called the Honey Badger BFT protocol. It's an asynchronous protocol that relies on a cryptographic component called the common coin. And soon after it's published, it was found that it contains a very subtle liveness bug. So in this work, we especially study the problem of formal verification of these asynchronous consensus protocols. We introduce shared distrib, which is a framework formalized in ROC for defining probabilistic I/O automata, and we support the parallel and layered composition of these automata. And we use this to formally model asynchronous consensus protocols, and we show how to prove probabilistic liveness of these difficult protocols. And concretely, we deliver the following result. We give you a formally verified asynchronous binary agreement protocol that's implemented as from a modification of the Honey Badger protocol, which is known to be buggy. So I'll first give an introduction to the features of shared distrib. Then I will introduce the approach we use to prove almost sure termination of our particular protocol. So in shared distrib, we represent probabilistic I/O automata as transition systems over distributions of states. And we represent each distribution as a list of a state and a probability value pair. And we allow two kinds of transitions, small step transitions on these systems. We call them split and action steps. In a split step, you select a particular state element in your distribution, and then you split it into multiple elements with the total probability summing to the original probability, but you don't change your state. This is usually a probabilistic stuttering step. And the action step is the place where the actual state transitions occur. And this can also be probabilistic. And since this is I/O automata, we further divide the action steps into 3 kinds of steps, which we call opponent steps, proponent steps, and the local steps. The opponent steps is basically you receive some invocation from upper layer application. And the proponent step is you return some information to the application. And all other steps which are invisible to the upper layer is called the local steps. And we simply model everything that's about the Byzantine processes as local steps. And in this work, we assume that the automata state is completely transparent to the adversary. So any I/O about the Byzantine state processes can be modeled as local steps. And instead, we support 2 kinds of composition, which is parallel composition and layered composition. In parallel composition, you let the automata execute in parallel, whereas in layered composition, you define overlay applications of your automata. So here's how layered composition looks like. You have your underlay automata, and then you can define how honest processes interact with the underlay. And you can layer this to many layers. So with this, if we look at the proof architecture again, if you look at this figure horizontally, you will see these copies of the instances of a graded Crusader agreement. And these represent individual rounds of the protocol. And that's a horizontal composition. Whereas if you look at this figure vertically, you will see that we are implementing GCA from common coin, and then binary agreement on top of an infinite number of rounds of GCA. And that's layered composition. To do liveness proof, you need one final ingredient, which is you need to work with infinite traces of these I/O automata. So we handle this challenge by segmenting an infinite trace into a sequence of asynchronous time steps. So you recall that in the asynchronous network model, even though you don't have an upper bound on message latency, you still assume that messages must be eventually delivered. And so you can define a time step as a period of time where all your messages sent before the time step are delivered by the end of the step. So this is what we do. We represent the execution as a tree structure like this. And then if you look at this horizontally, then every step represents a time step. And so you look at how a single state element splits probabilistically over a time step, which represents the process of delivering those messages. And then you take a snapshot of the tree at every time step, and you represent your liveness conditions as safety conditions over these time steps. So that's so far about the features of shared distrib. In the following, I will give you a very quick introduction about how asynchronous agreement actually works. It relies on a cryptographic component called the common coin. It's a global random bit that's not revealed until a majority of processes agree to reveal it. How you obtain this common coin is a difficult problem in cryptography, but here we just assume it's an ideal black box. Now, it turns out if you have this common coin, then there's a very easy way to do binary agreement. Basically, you first collect a set of valid inputs, and then you flip the common coin to get a global random bit. And now you compare your input set with your global random bit and make a decision. And there's lots and lots of protocols designed roughly based on ideas similar to this one, but this is basically how Honey Badger works. Now, it turns out for this idea to work, you really need the collection step, the first step of collecting these valid inputs to have a property called a binding. And if you don't satisfy this binding property, then there is a way for the adversary to rearrange the network message delivery so you never get liveness. And that's exactly the liveness bug of Honey Badger. So what we did is that we implemented a modified version of Honey Badger binary agreement part that fixes the original liveness issue in our shared distrib framework. And then we have to prove that this fixed version really satisfies the liveness property or the probabilistic almost shared termination. So here's the exciting part. How do you really prove that your protocol is probabilistically live? We give you a simple template for AST proof, which we call template hope termination hope functions. Here's how it works. You define a state function on your transition system which satisfies the following three properties. First, it's always bounded between 0 and 1 and represents a probability value. Intuitively, it's a lower bound on the probability of termination starting from a particular state S. Now, you define two conditions, P and Q, such that if your Q is true, if your P is true, then your state function is always an indicator for Q. And also, this function has to be a sub-martingale, meaning over each probabilistic step, the expectation of this hope function should never decrease. And with these conditions, you can now invoke the optional stopping theorem. Basically, if you set your stopping time to be the time where P becomes true, then at that time, the expectation of your hope function becomes exactly the probability that Q is true. In slightly more detail, here's how you apply this template to asynchronous consensus protocols. We first fix n to be a constant, and then we let Q to be the property that either the protocol has terminated or all honest processes have completed the first n runs. You can then prove deterministically that this Q property will be eventually true. And this is usually very easy using the traditional tools of deterministic liveness verification. Now, you then set your P property to be the condition required for the protocol to terminate. And it turns out for Honey Badger, this P property is that at least 2 of the first n runs needs to reach a certain convergence property. Now, what we do is we define a hope function fns for every constant n. And we prove that this fns function is a hope function that satisfies the required properties on the previous page. And therefore, if you start from the initial state S0 and you complete the first n rounds of agreement, you can use OST to harvest the fact that your termination probability is at least Fn S0. Finally, you take the limit as n goes to infinity, and you immediately get your almost sure termination result. We are, of course, aware that there's another line of thought on how to prove AST, which is using ranking supermartingales. But our experience has been that if you use the OST approach, then it's easier to derive quantitative liveness results. For example, we have a proof of the expected termination time. So to conclude, we introduced shared distrib, and we gave a foundationally verified safety and probabilistic liveness proof of asynchronous binary agreement, and we are actively extending this approach to more complex protocols. Thank you.
We are back on time, so we have plenty of time for questions. Please step up to the microphone or raise your hand if you'd like me to run the microphone to you.
Thanks for the talk and nice work. I'm interested in this layered composition thing that you're talking about. Could you say more about how that operation, that automata operation works, the layered composition operation?
Yeah, so remember that we have your IO automata has these three kinds of action steps called opponent, proponent, and the local step. Now, in layered composition, what happens is that you specify how these honest processes work by making these calls and returns. So you specify that under some condition, this honest process can make an invocation on your underlay, and that would be an opponent move from the perspective of the underlay. And then this underlay, under some condition, it can return some information to the honest process, and that's a proponent move. And then layered composition is basically defining a composed transition system that puts together all these transitions.
I see. So the proponent moves are the arrows, the downward or the upward arrows here?
Opponent is going down, and the proponent is going up. And these names come from game-based semantics.
Got it. Thank you.
Yeah.
I know the common coin is a black box for you, but are you sure that your common coin can be implemented?
Yeah, I can show you the formal definition, but we checked with the people in the cryptographic community, and it should be fine. Basically, you first, let me show you the paper definition. Yeah, so basically you have here, so you have a list of processes which called the open coin command, and then if this exceeds a certain threshold, the adversary can now call reveal coin, and then if you call reveal coin, then it randomly chooses a value from the given distribution, and that's our common coin. And we showed this to cryptographic people, and they think it's fine.
We're just going to start setting up the next talk, but we still have time for questions. Unfortunately, this means no more scrolling on PDFs for you.
All right, very interesting, thank you. I guess a couple of questions. First, if there is a bug in the protocol, what's the nice way to show actually that almost sure termination doesn't hold, or is there a nice way?
Sorry?
If the protocol is not correct, if you have a bug,
yeah.
What's a way to show that almost sure termination doesn't hold?
Well, if it doesn't work, then it's impossible to define the hope value function, because we have a formal theorem that if you have such a hope function, then it has to terminate with that probability as a lower bound. Concretely, I think there's a line of work from Nathalie Bertrand, and they are basically using parametric model checking to exhaustively explore the state space to see if to compute a lower bound for the termination probability. And if you read it, we can discuss more. It's offline, but there's some technical difficulty of their work, which our work handles.
Is there time for one more? No?
Let's thank the speaker one last time. Unfortunately, there's no time for follow-up. Great. Next up, we have Elaine giving us a talk about the implementability of global protocols. Take it away. And you need a microphone.
Hi everyone, my name is Elaine, and I'll be telling you about a network parametric solution to the implementability problem for global protocols. So let me start by introducing global protocols using the example of a task delegation protocol. So we have here 3 participants, a server and 2 workers, and the goal is for the server to delegate a task to these 2 workers. Among these 2 workers, one of them is diligent, so upon receiving a workload, it will immediately service the workload and send it back to the server. The other worker, however, is lazier, so it may send back the entire assigned workload, or it may choose to delegate part or all of its workload to the diligent worker, worker 2, in which case each of these 2 workers sends back half of the workload. Even in the case that the server decides a priori to split the workload between these 2 workers, the diligent worker will of course return it right away, but the lazy worker may still choose to assign its portion of the workload to the diligent worker and have it return it to the server. So global protocols go by a number of names. They were first introduced in the form of high-level message sequence charts, whose visual formalism we're using here, and they're also featured prominently in contemporary programming language frameworks like session types and choreographic programs. The essential features that are common to all global protocols are the following. The first is that the behavior of all participants is specified jointly from a bird's eye view. So in this message sequence chart diagram, the vertical lines describe each of the 3 participants, the server and the 2 workers. Secondly, the sending and receiving of a message is specified atomically. So the horizontal arrows that connect the server and worker 1 in this case, labeled by a payload, describes the atomic and instantaneous exchange of this message half between them. Finally, the control flow in a global protocol is also global. So in this protocol, the various branching points correspond to decisions made by either the server or worker 1 as to whether to further delegate work. Global protocols inspire a top-down verification methodology in which they are used as blueprints from which to synthesize correct by construction distributed implementations. So we desire to synthesize one local implementation for each participant in the protocol so that when they are run in a distributed system, they are free from deadlocks and conform to the global specification exactly. As with any synthesis problem, one needs to first answer the question of realizability, which in our setting asks whether the assumptions that we made in the global protocol abstraction, namely that there are no message channels, so messages cannot be reordered or delayed, they are instantaneously sent and received. And also there is a global coordinator that ensures that all of the participants together follow the same branches. Realizability asks whether these assumptions are realistic to make in a distributed setting, in which the only way that participants can gain information about the global system is by sending and receiving messages. In fact, our running example contains sources of non-implementability. So let's look at just 2 of these branches in the protocol. In the first one, server sends worker 1 the full workload. Worker 1 delegates half to worker 2 and completes half of it itself. In the right branch here, server splits the workload between worker 1 and worker 2, but worker 1 nonetheless decides to delegate its portion to worker 2. So worker 2 first services server's half and then services worker 1's delegated half. So these are 2 scenarios that are described from a global point of view, but let's have a look at what really happens in a distributed setting. So in a distributed setting, server first sends the full message to worker 1 receives it, and now worker 1 proceeds to send a message to worker 2. So worker 2 has this half message that is available for it to receive in its channel. Now let's look at the second scenario. So again, server sends a half message to worker 1 receives it, and now both server and worker 1 want to send half messages to worker 2. These 2 sends are independent, so the network can reorder as well as arbitrarily delay them. In this case, the network has first delivered the message from worker 1, and the message from the server is still in flight here. From the perspective of worker 2, these two branches are identical. The only thing that worker 2 can observe is that there is a half message from worker 1 that is available in its channel for it to receive. However, depending on which of the two branches the other two participants took, worker 2 is supposed to perform different actions. So in the left branch, worker 2 is supposed to immediately reply with a half message, whereas in the right branch, worker 2 is supposed to wait to receive first the message half from server, service that, and then service the message from worker 1. And performing the opposite action in each of the branches will lead to either a deadlock or a violation of the global protocol. For that reason, this global protocol is not implementable. So we could repair this protocol by changing the message payload in the left branch from half to delegate. So this way, when worker 2 receives a delegate message, it knows that it should immediately reply, whereas when it receives a half, it should wait. Unfortunately, this is not a universal repair. And to see this, let's take a closer look at just the right branch. So in the right branch, we have two messages that are both in flight, two half messages to worker 2. And the network can reorder them, so it schedules the message from worker 1 first, and then the message from server. Now, worker 2 knows that it is supposed to service the server's half first, and then worker 1. Whether it is actually able to do so depends on the particulars of how these two messages that are in flight are buffered. In particular, if both messages are buffered in the same FIFO queue, a la mailbox communication, even though worker 2 knows the order in which it's supposed to receive and process these messages, it is unable to do so due to network reordering. So this will lead to a deadlock in the system. Hopefully, these examples make it clear that the question of implementability should be considered to be parametric in a choice of network or on a set of network assumptions. And our goal in this work was to propose a single characterization of implementability and a proof of its preciseness that reasons about all different asynchronous networks at the same time. So the first question that we need to answer is, what exactly is an asynchronous network? And the literature's partial answer to this question is that, well, there are a lot of different models of asynchronous communication. So to tour you through some of the most common models, we have mailbox, as we've seen, in which all incoming messages from different senders are buffered into a single FIFO queue for the receiver. This is implemented in actor-based programming languages like Elixir and Erlang, and decision problems like synchronizability have been studied specifically for this model. The dual of mailbox is senderbox, in which all outgoing messages from a participant are buffered into the same FIFO queue. This can be found in work-stealing paradigms in parallel programming. Another common network model is what we call a mono bag. So here, all messages are buffered into a single multiset that all participants have access to, and this is commonly assumed by consensus protocols. By and large, the most common and popular communication model is peer-to-peer FIFO. So here, we have 2 channels per pair of participants in the protocol. This is ubiquitous in theoretical results from concurrency theory, as well as commonly assumed in verification frameworks. So we classify networks along 2 dimensions. The first is a communication topology that maps ordered pairs of sender and receiver to buffer data structures. The second dimension talks about what the buffer data structure is. In particular, it's characterized by partial insert and remove operations. So this is what is containing the messages. And with that, our distributed implementation model is a set of local implementations, one for each participant, that is connected and communicating across a network architecture defined in terms of these 2 components. With this, we are able to give a formal language semantics to network architectures. And we do so by removing the influence of local implementations on the set of behaviors that the system is able to execute, by setting each local implementation to be the universally accepting language. So now the only behaviors that can be executed are entirely dependent on the network architecture, the order in which it allows to send and receive messages. So this way, a network we define as a formal language. It's the set of finite and infinite words that are executable by the universal communicating system under a given network architecture. So we have an answer to what an asynchronous network is. Now we want to design this implementability characterization. And our starting point is an existing precise characterization that is specifically for peer-to-peer FIFO communication. In a nutshell, this characterization says that when a participant is in a state of confusion about which of two states it could be in, it is allowed to send a message that is allowed by both states. It is allowed to receive a message that will help it to uniquely distinguish the two states, but it is not allowed to choose between sending or receiving a message if it doesn't know which of the two states it's on. So this was proven to be a equivalent characterization of implementability, and we generalize these conditions in two ways. The first is that the ability to receive a message is highly dependent on the network architecture. So we call the new condition generalized receive coherence that depends on a parameter A, which is the network architecture. We add a fourth condition, which intuitively says that insufficient information is the only cause of possible deadlocks or protocol violations. So in a setting where participants have perfect information, the protocol is not allowed to contain runs that would nonetheless deadlock. And in fact, we saw violations to each of these two new properties. So the first scenario where worker 2 doesn't know whether to reply or to wait is a violation of receive coherence. And the second scenario in which the system deadlocks in spite of worker 2 knowing exactly what to do is a violation of prefix extensibility. So we have our implementability characterization. We need to go back and qualify the asynchronous networks under which this characterization is precise, right? Because it doesn't obviously work for all of them. The way that we do this is we define a set of axioms or channel compliance facts that talk about the network as a formal language. So these are algebraic in nature, and they say if certain words are in the language, then certain other words must also be in the language, and so on. And so with this, we have achieved our goal of having a network parametric characterization. So we prove that for any network architecture that satisfies these algebraic axioms, our generalized coherence conditions are precise with respect to implementability. This is, however, not a fully satisfying solution. Suppose I wanted to use the framework to target communicating mailbox systems. So what I need to do is I need to prove these channel compliance facts for the mailbox system. And now suppose that I wanted to also target sender box communicating systems. Well, because these are two distinct network architectures, I would need to reprove all of my channel compliance facts. And this is oftentimes non-trivial. We would like to be able to ignore the effect of varying communication topology in determining what networks are instances of our framework. And this is exactly what we do in the final step. So we distill our channel compliance facts down to a set of simple operational axioms that talk only about the buffer data structure. So these describe the insert and remove behavior of buffer data structures. Looking at B1, for example, this says that insertion is a total operation. This immediately rules out bounded channels. Looking at B4, it says that if I can remove from a buffer, then inserting another message doesn't prevent me from being able to remove that message, which immediately rules out priority queues and stacks. But with the same ease, we can conclude that FIFO queues and multisets satisfy all of the aforementioned buffer axioms. So this new methodology says that we prove B1 through B8 once and for all for FIFO queues and multisets. And from this, we can obtain that mailbox and sender box and monobox peer-to-peer FIFO bag are all instances of the framework without having to establish any new proof obligations. As a freebie, we also obtain that heterogeneous network architectures that mix the use of FIFO queues and multisets are also instances of our framework. We implemented our decision procedure in an extension of a tool for peer-to-peer FIFO called Sprout. So Sprout additionally takes as input a choice of 5 common homogeneous network architectures. It implements a sound and complete reduction to MuCLP and discharges the obligations to a state-of-the-art MuCLP solver. We show that Sprout does not sacrifice efficiency despite supporting more network architectures. A more interesting aspect of the evaluation is that by looking at the average verification times of 3 network architectures, we show that these times track the theoretical relationships that we were able to establish among classes of global protocols that are implementable by each of these 3 network architectures. So intuitively, the smaller the set is of A, implementable global protocols, the more difficult it is and the longer it takes to verify implementability. So that's all that I have for today, and I'm happy to take any questions.
As with before, please come up to the microphone if you have questions. Unlike before, I don't have a runner mic, so you have to come up.
Perhaps this is obvious, but I didn't find it. So it makes sense to me that given proving all of the buffer axioms for FIFO queues and multi-sets, that you would be able to recover the rest of the behavior. But the heterogeneous mix of either the bags and the queues does not seem the fact that you can mix them doesn't seem obvious to me. Especially when you said that if you have to make the decision between receiving a message or replying, that things kind of fall apart. So what is it that is allowing the heterogeneous mixture of different message dispatching models to sort of join up to maintain these properties?
So when we prove the step from basically that the B's imply the F's, right? We are universally quantifying over all possible communication topologies. So what is sort of dispatching this obligation is showing that these data structure assumptions are sufficient to give us these formal language theoretic algebraic axioms.
So that part makes sense, but what is it about the composition of the different, because you have the buffer axioms and you say okay, each of these individually satisfies it. Does that always mean that any composition of those network topologies meets those axioms?
For this set of axioms, yes.
Okay.
And some of these, for example, if you look at the first one, this is like a simple rephrasing of the totality of insert, right? Just phrased as a sort of algebraic property. So it says if W is channel compliant, then you can always append X, which is a send event, and this stays channel compliant. So for some of them, the correspondence is obvious, and for some of them, less so. There isn't sort of a clean mapping.
Hi, excellent talk, thank you. I wonder if you could talk generally about message ordering guarantees in asynchronous, and I know there's an impossibility, but I wonder if your system has considered synchronous checkpointing for causal ordering versus FIFO ordering, and if you could.
Right, so causal ordering is an interesting one that doesn't cleanly fit into our framework because it is not sort of architectural. So you can't purely define it as the cross product of some choice of data structure and topology. As for asynchronous, or in general, what I can say, for example, we don't support message dropping, only reordering and delay. So that also rules out a large class of asynchronous models in general.
We have time for about one more question while we wait for the next speaker to set up. I have one last question, if that's all right. So we often see in network architectures that their bounded queues are a bit fundamental. That even if we modeled something as FIFO, fundamentally there is a bounded buffer, and that the way we get unboundedness is by applying back pressure. Does this violate the assumption, or is sort of this back pressure based theoretically bounded, but in practice not, wind up working out for your model?
So our framework does not support bounded queues in any way, because that would violate the totality of insert. However, if you had a communicating system with bounded channels, this would be a finite state system. So this sort of suggests a different set of techniques to solve the problem.
Great, let's thank the speaker one last time. Lastly, for the session, we have Emma talking about the next iteration of Netcat. Take it away.
Hello. Does this work? Cool. Hey everyone, I'm going to be talking about weighted netcat, a programming language for quantitative network verification. And to start off, I'd like to talk about network verification more broadly. And for that, I have a network here made up of hosts, which are the computers connecting to this network, and switches, which are the actual pieces of hardware that will be delivering our packets of network information. And each of these switches is going to be configured with its own forwarding tables to decide how to actually forward packets to their next destination. And this can be based on a variety of protocol header field or of packet header fields, such as source and destination. It can also be protocols. For simplicity, here I'm saying that switch 1 forwards packets based on source and destination. So if it receives packets sourced from host A, destined for host C, it'll forward them to switch 3. And network verification is, for our purposes, being able to answer questions of reachability and connectivity in these networks in a fully automatic way. So for example, for a network such as this one, being able to verify, can all hosts deliver packets to one another? And although this question might seem simple at first glance, it actually becomes quite difficult to reason about, as each of these switches are going to be working together compositionally and as we increase the switches in our network. So quantitative network verification is then kind of taking this a step further and recognizing that there's a lot of quantities that are going to arise naturally in networks that are going to be relevant to these network verification questions. So for example, here I have now reliability. So each of these switches has some instrumented packet loss from which we've determined their success rate, with which they're going to successfully forward packets onto the next switch. And now the questions that I want to verify are going to take shape of, for example, does all traffic get delivered with at least 90% reliability? And I'm saying quantitative here because there's many, again, quantities that show up. So beyond reliability, I could also talk about properties like latency. So the links between these switches might have some incurred latency that has been instrumented when they're actually forwarding packets. And again, I want to verify these questions with these quantities in mind. So can host A deliver packets to host B within 5 milliseconds? And weighted netcat is an extension to a programming language called netcat, which gives us a very nice framework to actually represent a network such as this one as a program and be able to automatically verify questions such as the first one that I have here. So our goal with weighted netcat is to sort of lift this to a quantitative setting to be able to actually verify questions such as these two. So since weighted netcat is an extension to netcat, let me tell you how to actually model network behavior in netcat and by extension weighted netcat. And for that, I have a smaller network here with 4 switches and 2 hosts. So let's focus on switch 1 and say that switch 1 forwards packets destined for host B through switches 3 or 4. As a program, this would be this if statement here that I have that checks the field DST, and if it's host B, then we will update the field SW to 3 or to 4 with this choice operation, where we're using the field SW to keep track of the actual location of the packet in the network. And we can encode the forwarding behavior of the other switches in a similar way so that the forwarding behavior of the entire network is then going to be the composition of these parts. If we're at switch 1, we execute switch 1's forwarding behavior, and so on. And the network itself is then going to be the iteration of this forwarding logic. So when the network receives a packet, it is going to continuously process and forward a packet until it might be ready to exit the network. And again, this kind of gives us a way to both model and verify questions like, can all hosts deliver packets to one another? But our goal is to be able to kind of model quantitative network behavior as well. And what we do in weighted netcat is we have this piece of syntax, R-O.P, which is called weighting, which intuitively says do P with a weight of R, or run P with a weight of R. So returning to this example of reliability, what we would do to modify this program would be to say, now when we execute each switch's actual forwarding behavior, we will do so with the associated weight. So P1 incurs a weight of 98% because it has a 98% reliability. And returning to this example of latency, let's say switch 1 forwards packets to switch 3 with 2 milliseconds of latency and to switch 4 with 4 milliseconds of latency. How we would modify the program now would be to take this part where we actually update the switch field, which again is modeling that forwarding action, and give it that weight. So updating to switch 3 takes 2 milliseconds. And notice how based on kind of what part of our syntax we're kind of weighting different weights that can show up in different parts of the network. I also want to talk about this choice operation, which in our setting becomes a weighted choice. And based on kind of what we're taking this to mean, we can be modeling different quantitative network behaviors. So to elaborate a little bit more on what I mean by that, let me talk about our weights. And a weighted netcat is going to be parametric on a semi-ring, and its weights, as well as operations for weighting and choice, will be drawn from this semi-ring. And a semi-ring is a set with addition and multiplication and identities for these. And intuitively, we use a semi-ring because there's this notion of combining or accumulating weights along a path, which is multiplication, as well as a notion of choosing between alternate paths, which is addition. And again, based on sort of the choice of semi-ring, we are going to be modeling different quantitative behaviors. So more concretely, let's talk about latency, for example. If I want to model best case latency, I would use what is called the tropical semi-ring, which has natural numbers as its elements, and its weighted choice is going to be minimum. So this is taken to mean I want to say what is the better latency of my different branches. So I'm getting a best case analysis on latency in the network to say across all network paths, what's the best possible latency. And path accumulation is going to be addition. So along a network path, I want to be adding latencies. Alternatively, for reliability, we would use what is called the Viterbi semi-ring, which has probabilities as its elements, and its weighted choice is going to be max, which is taken to mean choosing the better reliability. And now path accumulation is going to be multiplication. So along a network path, we want to multiply all of the probabilities of successful forwarding. What if we want to model worst case reliability instead? For that, we use what we call the probabilistic union semi-ring, which still has probabilities as its elements and still has max as its weighted choice, except this is now taken to mean choosing the worst failure rate. And for that, what we do is we shift our perspective a little bit, and we say if a packet has a 96% success rate, it's equivalently going to have a 4% failure rate. And under this perspective, we now have a kind of analysis of sort of the worst case reliability in the network. And our path accumulation is going to be U+, which is the probability of the union of two events. So along a network path, what is the probability of any one action failing? And beyond modeling, I also want to talk about the actual verification that we do with weighted netcat. And for that, I'll talk about our semantics at a high level. So intuitively, a program in weighted netcat is going to be interpreted as a function that takes some input packet and assigns a weight to every output trace. So if I interpret a program, I give it a packet and a trace, I'm going to get a semi-ring element, which is going to be the weight associated with this network path. And I should note that this semantics is going to be purely functional. I have an input packet, I have an output trace, and as a result, in this semantics, we're not actually modeling behaviors like queuing or congestion, which can actually, of course, affect these quantities, but the semantics is still suitable for many quantitative network verification questions for a few reasons. For example, modern network hardware has made packet level interactions less important, allowing us to model these at a coarser granularity, as well as many quantities that we're talking about are also going to be independent of behaviors like congestion, like reliability or security. So then the quantitative verification questions that we do target in weighted netcat are two, the first one being our safety, which is, does all network traffic have weight at most R? And this corresponds with our question from earlier, does all traffic get delivered with at least 90% reliability? And this fits nicely for settings where we want to have some upper bound across all network behaviors on our quantities. And semantically, this would be sort of having an upper bound on all input packets and output traces. And dually to that, we have what we call R reachability, which is, does there exist network traffic with weight at least R? Which is going to correspond to this earlier question, can host A deliver packets to host B within 5 milliseconds? And again, this being kind of finding some input packet and output trace that satisfies this minimum weight. And for actually being able to verify these two questions, to do so kind of in a fully automatic way, if we were to do so directly, we would need to compute the semantics for infinitely many input packets. And what's more, we'd need to do so for programs with potentially unbounded iteration. So the approach that is typically taken for this is to use automata-based model checking, where we derive some automata model of our network and then check this automata. So there's a challenge here in our paper, which is that traditional weighted automata don't quite fit the setting of weighted netcat. So the reason for this being that weighted netcat has stateful packet transitions. And what I mean by that, I can kind of explain with this program snippet where I'm saying if the field dest is B, then I will update the field SW to 3. For this to be a valid transition in an automaton, I need to know that the previous packet that I'm coming from had the field B mapped to B. So we need this notion of keeping track of the previous packet state in our automaton, which doesn't quite fit with a regular weighted automata. What we do is instead we develop our own automata model that we call WNetCat automata, and let me explain sort of what that is. And for that I have a finite automaton here with 3 states. I have an input state S1 and then accepting states S2 and S3. And this automaton is going to have weights introduced. So entering at state S1 incurs a weight of 1, where let's say we're working with a tropical semiring. And the transitions of the automaton are going to be these transitions that consume 2 packets at once. So this is going to be kind of saying I'm going from a previous packet alpha to the next packet pi. And the transition will have a weight of 2. And our exit states are now also going to have packets that they're consuming to represent kind of this notion of going from the previous packet to the final packet. So this is saying exit the automaton from a previous packet pi to a final packet C with a weight of 3. And filling in the whole automaton, let's talk a little bit about the language accepted by this automaton, but focusing on this bottom path here. So this automaton would accept the string alpha pi C with a weight of 6, 1 plus 2 plus 3. And notice how here is where this notion of the previous packet state comes into play, where for this to be a realizable path in our automaton, we need to have the actual packet states match up so that this can be a valid trace in our network. And similarly for this top path here, it would be the string alpha beta pi, saying that we start at packet alpha, continue on to packet beta, and exit with packet pi, and so on and so forth. But what I want to note is that the language accepted by this automaton is then going to be made up of complete network traces. So these are going to be strings that can describe every packet state in our network as we are stepping through our program. And each of these traces is going to be associated with a weight, which kind of has this nice correspondence with the high-level semantics of a program that I talked about earlier. But there's this nice thing that this automaton gives us a finite description of computation, so we can actually use this automaton for our verification questions instead of computing the semantics of a program directly. And this is exactly what we do for automatic verification, is we take a program and we compile it to its corresponding automaton. And I won't go over the compilation procedure, but the takeaway is that we show that the semantics of both of these coincide exactly. So the theorem that we derive from this is that the semantics of any program can be computed by compiling it to its corresponding automaton. And kind of a further implication of this is that the automatic verification of our quantitative verification questions can be done at the level of WNetCat automata. However, there's sort of one final wrinkle here, which is that in the presence of weights, several properties of automata are known to in general become undecidable. So we still have to actually show that these quantitative verification questions are decidable for our automata. So finally, in our paper, we also developed decision procedures over WNetCat automata that establish the decidability of these properties. So our safety and our reachability, with our safety again corresponding with this question. And if this property is false according to our decision procedure, then we additionally provide a trace violating the property, which can help you for actually debugging your network and reconfiguring it so that you actually satisfy our safety. And similarly for our reachability, if this property is satisfied, we give you a trace showing that this property is satisfied so that you can perhaps reconfigure your network to actually give priority to this network path. And although I've focused on reliability and latency in this talk, I should note that the decidability of these decision procedures and our paper is actually generic over a broad class of semirings that actually capture a broad array of quantitative network verification questions. So I left out a few details, in particular our compilation as well as our decision procedures. So please see our paper for those, as well as a case study kind of showing the applicability of weighted netcat. But with that, I'd be happy to take any questions you might have, and thank you for your time.
Can I ask 2 questions? Okay, so you said that a broad class of semirings. So the history of using semirings for talking about network problems is a very old one. It's like goes back 65 years at least. You said a broad class of semirings. So any particular semirings that you don't deal with? Why doesn't every semiring?
Yeah, we have some restrictions on our semirings, like in particular, like omega continuous semirings. Okay. So they have to have suprema.
So you needed some kind of monotonicity and continuity. Probably.
Yes, okay. And for our decision procedures, we also need the choice operation for our safety to have this mapping with suprema as well, because there's this notion of sort of choosing across the network, for example.
Okay.
Yeah.
The other question is, are there any problems which are decidable for weighted automata which are undecidable for your kind of WNetcat automata?
Not that I know of, though. We sort of base our approach to showing the decidability of these procedures on decision problems for weighted automata, so I would hope that we could map the two. Yeah.
Right.
Thank you.
Which
yeah.
Great talk.
Oh, thanks.
Hi, Jack Senzak from Yale. Thanks for the great talk. It looks like the question I was going to ask is actually in your future work notes. So I know in previous PLDIs there's been work on symbolic representations of these automata. I know there's certain data structures like BDDs, for example, that are polymorphic over semirings. So I was wondering if you could, say more if you thought about that or not.
I am not directly involved with the symbolic representations of automata, but I could point you to people who are. Yeah.
Thanks.
Yeah.
We lost our last questioner. You can come back. Come on up.
Okay, thanks for a great talk. And now a very small question that I think you have considered probability, and currently in your setting, since you are doing semiring, I'm assuming that your probability has no correlations and dependencies. Have you considered adding these things in your system?
Could you repeat the question, sorry?
So have you considered adding the correlations, dependencies in your probabilistic system?
So like actions based on the weights, you mean, or?
I think another way to put that is, if you take this link, if this link fails, then it's highly correlated the next one will fail.
Yeah.
That kind of correlation.
Yeah. So I have thought about this a little bit because it's a little weird that there's this kind of sequential path, but and the semiring also maybe is a less familiar semiring, but it has a mapping to like the Arctic semiring, in the same way that the Viterbi semiring has like a mapping to the tropical semiring, so it sort of fits in the setting, but it would be interesting to think about sort of these dependent probabilities, but I think we would have to change a bit of our semantic model for this. Yeah. I don't know
see.
if that.
Thank you for answering.
Yeah.
All right, I have one last question, which I will take chair's prerogative to ask it. We have time, I promise. I've seen a lot of work previously that seems to do similar things via probabilistic netcat. I'm curious if you can comment on your relationship between those two lines of work.
Yeah. So we have like a result in our paper also that we sort of consume traditional netcat and the guarded fragment of probabilistic netcat, since the probability semiring is partial, so it doesn't quite map. But if you focus on, instead of kind of unguarded choice, having guarded choice, and while loops instead of unbounded iteration, we would consume that fragment of probabilistic netcat. Yeah.
Great, that's the result you want. Well, let's thank the speaker one last time. And unless I'm about to be very embarrassed, that's the last talk of this session. Thank you all for enjoying distributed systems, and we'll see you after the break.
Let's start. Welcome everyone. My name is Mukund Raghotaman, and this is the session on abstract interpretation. First talk of the session will be given by Jihan Gu, who is a first-year PhD student at UIUC, and she'll be talking to us about how to get an LLM to synthesize sound abstract interpreters.
Thank you, everyone. Hi, I'm Jihan. Thanks for coming. And I'll be presenting our work, Cell, Sound Abstract Interpreters with LLMs. This is a joint work with Avajong Sync and Professor Gangan DeepSync. We start with the motivating example in reasoning about nonlinear operators, the ReLU function here. Suppose we want to verify the property that all the outputs of the ReLU function is always non-negative. Therefore, the most straightforward way is to enumerate all execution traces. However, the issue is there will be infinitely many inputs, which makes this method impossible. Therefore, a natural choice is to apply abstract interpretation, which is actually the only automatic approach we can adopt when we are reasoning about the highly nonlinear functions, despite we use the ReLU, the piecewise linear function here. So in this case, we can apply abstract interpretation and then categorize the input X into two cases. And then we approximate the box domain through the program until we get the approximated output for us to do the verification. And there are many more highly nonlinear functions apart from ReLU, such as JLU and ELU, which are usually commonly used in many downstream tasks. For example, the neural network verification. So the key component that enables the correct propagation in the neural network verification is a sound abstract interpreter, which is the composition of many sound abstract transformers. And to construct such kind of sound abstract interpreter is not an easy task, because we can see that for each abstract transformer, we need to go through three phases: the specification, verification, and implementation. We can get a sense of the difficulty by just looking at this example. This is a manual derivation of the Har-Sigmoid function in the de Pauli domain. And that is the Har-Sigmoid function, which is a piecewise linear function. So we can see that even for a single operator, it requires multiple pages of case analysis, geometric reasoning, and soundness proof. So there are many works that are trying to automate this pipeline. From the first phase specification, there are works focusing on symbolic synthesis and optimization-based methods, and so on. And to automate the following two phases, in 2025, our group came up with the first automatic verifier, proof sound, which is based upon the domain-specific language constraint flow. So we can automatically verify the soundness with SMT solving. And to automate the implementation phase, we come up with the compiler Newton, which can automatically translate the abstract transformer in the domain-specific language from PyTorch code. And then you can use that PyTorch code wherever you want. So they're all pretty exciting, I would say, but that is far from enough, because there are two main problems. The first one is those modules are still isolated with each other, meaning that if we want to really automate this pipeline, we need at least 3 experts working on these 3 areas. And even we have already lowered the barrier here by providing a specification, a domain-specific language constraint flow, but that still needs a lot of expertise to write those domain-specific language. And the second problem is much more effort should be put into the first synthesis phase, because the current work, they might suffer from the limited generality and imprecision problem. So among everything, the first question we ask is, can we have an end-to-end automatic pipeline? And our answer is yes. We come up with the Cell, sound abstract interpreters with LLMs. With Cell, the only thing you need to do is to input the keywords in the simple natural language to tell us which operator in which domain do you want. And then Cell can provide you with the sophisticated and completely sound abstract transformers. Not just mathematical expressions, but a valid domain-specific language, which can be later using our compiler Newton to translate it to the PyTorch code. And then you can integrate this PyTorch code within any downstreams without any extra efforts. And Cell is a one-size-fits-all framework, meaning that we can handle multiple abstract transformers in terms of multiple domains. So let's go into details of the design. As LLMs become pretty impressive these days, we want to make use of the potential. Therefore, the first question that pops up in our mind is, can we just simply use the naive prompt engineering? Of course, the answer is no. Otherwise, this work won't come to PLDI today. So there are two reasons. The first one is we require strict soundness guarantee. We briefly recall the formal definition of soundness here. We choose this oracle, which says that for all abstract elements in the abstract domain, the result we get by first doing the concretization and then doing the transformation should be less or equal to the result we get by first doing the transformation and then doing the concretization. So intuitively, it means that we should never miss any real behaviors. And there are two things in this oracle should have our attention. The first one is soundness must hold for all abstract elements, which will form an infinite space. And the second thing is each abstract element will abstract infinite number of concrete points. So at least these two infinity words kind of imply the difficulty of our task. And apart from this, therefore, a question that will naturally come up is, can we have something to help guide the LLM in the infinite space? And here comes our first key idea, that we come up with the principal function to measure the unsoundness. And the intuition behind this cost function is similar to that of the loss function during the model training, that instead of searching blindly, with this cost function, we can measure how far an unsound transformer deviates from being sound. And apart from this soundness guarantee, another guarantee we require is validity guarantee. This is because what we want is not just mathematical expressions, but a valid domain-specific language, which should be both syntactically and semantically correct. Therefore, combining these two requirements motivating our second key idea, that is, we formalize the whole synthesis problem as a constraint optimization problem. The objective here is to minimize the cost, but at the same time, we will enforce hard validity constraints. So now we can have a high-level sketch of our pipeline. We first prompt the model to get a set of transformers, candidates, and then we will pass it to our checkers to validate it against the DSL grammar. And then, in practice, this checker is lightweight and manually designed. We hard-coded 6 mistake patterns that are commonly observed in the early model generation stage in our experiments, such as typing errors, invalid constructs, and so on. So if a transformer fails this checker, then we will invoke an LLM-based repairer that attempts to fix it automatically. And then the transformer will be passed to the automatic verifier proof sound to finally verify its validity, and more importantly, to verify its soundness. If it's sound, then that's good. It will be output directly at the final result. But if it's unsound, then we will use a cost function to measure the degree of the unsoundness. So within this batch of transformers, we will choose a best unsound transformer based on 2 rules. The first one is it should have the smallest cost within this batch. And the second rule is it should have a smaller cost than that of the cost function during the last generation. And then this transformer will be passed to the LLM again to help guide the next round's generation. So we can see that the core of this pipeline is this cost function. Therefore, this is our final problem. How to design this kind of principled cost function? So we will illustrate our idea within a concrete example here. Say we want to synthesize the abstract transformer for the ReLU function in the box domain. We know that there are many trivially sound abstract transformers, but let's look at this one, the transformer that will always output the interval 0 to 1. It is correct for some inputs, but it is incorrect for some other inputs. For example, when the input is the interval 0 to 2, we can easily find some concrete points within the concretization of this interval that fails the soundness requirement. And same as the input 0 to 3, 0 to 4, and so on. We call all of these as counterexamples, which are essentially the abstract element that violate the soundness. And if we collect all of these counterexamples, we can form a counterexample set, A star. And this is exactly our first step. Now, if we want to measure the unsoundness of a transformer, we only need to measure the unsoundness degree of this A star set. which is equivalent to measure the contribution of each element within this star to the unsoundness and then do the aggregation. Therefore, the question is, how do we measure the contribution of each element, of each violating abstract element within this set? Do we simply let it equal to 1? We cannot, due to two reasons. The first one is the A star could be an infinite. If we let the contribution of each element equals to 1, then the problem is reduced to counting the number of the counterexamples, which is actually infeasible. The second question, which is more important, is it will fail to capture the different contributions of different counterexamples to the unsoundness. We can better understand the different contributions here by looking at these two examples. The first one is the counterexample, the interval 0 to 2, and the second one is the interval 0 to 3. So the reason that they are classified as the counterexample is because we can always find some concrete point lying in the sub-area of the concretization of these two abstract elements that violates the soundness requirement. And we'll visualize the sub-area here by the colorful shady region. So we can see that each violating abstract element will have different colorful shady region here, which reminds us that each violating abstract element will contribute different degrees of unsoundness. And at the same time, it prompts us that if we want to measure the contribution of each counterexample to the unsoundness, we only need to measure the contribution of each violating concrete points that lies in this area and then do the aggregation. For example, if we want to measure the contribution of this counterexample C1, the interval 0 to 2, it will be reduced to measure the contribution of each concrete point. For example, the concrete point here, x equals to 1.5. So how do we measure this concrete point? The reason that it is a violating concrete point is its output is not correctly abstracted by the output of the abstract transformer. Or let's illustrate it from another perspective. The output of the abstract transformer, which is an abstract element, will enforce several constraints, and the output of this concrete point will violate at least one of those constraints. So this tells us two things. The first thing is outputted abstract element from the abstract transformer corresponds to several constraints. And the second thing is, if we want to measure the contribution of each violating concrete point, it's equivalent to measure how much the output of concrete points violates those constraints. So in practice, when we are reasoning, when we are working on the numerical domains, we define two types of constraints, the scalar bound constraints and the phi bound constraints. And we define the measurement through the distance computation. For example, if we want to measure the violation of the concrete point x equals to 1.5, we only need to measure how much it is above the upper bound plus how much it is below the lower bound. So now we will have our finalized cost function, and this is the formalization. So more formal details can be found in our paper, but we can see that it is a highly hierarchical cost function. We first operate over the abstract elements, they operate over the concrete states, and in the end, we will operate over constraints. So it's totally principled because we only derive it based on the formal definition of soundness, and it is quantitative, it's a continuous measure, which is really helpful for the guidance. And in practice, as both the set A star and the concretization set are infinite, so we will use the weighted sampling to make it feasible. So now we will have a finalized version of our pipeline. We first combine the natural language specification with the historical generation to prompt the model, and then we enforce our validity constraint through our checker. And then we use the automatic verifier to verify the soundness. And in the end, we use a cost function to help guide the search. So this iteration will keep going on until we find a sound abstract transformer or reach a maximum number of attempts. And in that case, we will use a trivially sound abstract transformer as a fallback. We know that when we're talking about the abstract transformer, there were always two metrics. The first one is soundness, and the second one is precision. So we did not explicitly encode the precision information in our pipeline, but we do observe a decent precision of the result we synthesized in our experiment. And we believe it's because of two designs in our pipeline. The first one is our prompting design. So in our prompting, we provide a few short examples with good case distinctions and DSL constructions for common patterns, such as the tangent line and the second line. And this can help discourage the model from generating some trivially sound but loose relaxations, loose abstract transformers. And the second reason is because the implicit enforcement by cost function. So when we're doing the weighted sampling, the weight function we use will penalize violations near transition points more, which will encourage a correct case distinctions. And moreover, the cost function will as we talked about before, our domain-specific language patterns provide some common patterns such as the second line and the tangent line. Therefore, after we get a kind of precise but unsound affine, for example, the affine bonds, our cost function can penalize it until it becomes sound. So in the end of our experiments, we do the evaluation through 3 metrics: the efficiency, generality, and scalability. For efficiency, we observe that each synthesis will finish within around 2 hours maximum. And during this process, our cost function plays an important role and improves synthesis success. And in the end, the result we get consistently achieves high precision. Here are some examples. This is the decreasing trajectory of the cost function. The x-axis is the number of the iterations, and the y-axis is the value of the cost we got during, within that round. So we can see that despite cost function will help different models will provide different degrees of help in terms of different models because models have different capacity, but after all, it will always help the model to help the algorithm to converge. And this is the result we get. This is the synthesized hard-sigmoid transformer in the domain-specific language, which is not existed in the previous literature. And after we apply the compiler to translate that domain-specific language into a PyTorch code, this is what we can get. And this can be integrated into any downstream tasks without any extra effort. So in our experiment, we choose the neural network verification as our downstream tasks. And here are the precision results we get. We can see that for some operators which already have the existing handcrafted transformers, we can achieve the same precision, and we can synthesize more transformers which are not existed in the literature before with decent precision. And for the second matrix, generality, we test our algorithm to synthesize multiple abstract transformers for operators from linear, piecewise linear, nonlinear functions, and so on, in terms of different abstract domains, from the simple box domain to the advanced and compositional depoly domain. And we even test our pipeline to synthesize transformers for the first-order derivatives, and we found that they all work pretty well. This is an example of the synthesized JLU and ELU function. We can see that they all have very careful and good case distinctions and precise and tight bonds. So in the end, we test our scalability. So we found that the peak memory we use is only 650 megabytes, and we want to emphasize that you only need to synthesize once, and you can reuse whatever you get forever. So more details can be found in our paper, and our code is totally public to everyone. Please feel free to scan them and read it if you are interested. And we hope our work can inspire efficient abstract interpretation and make it more accessible to everyone in the community. Thank you very much.
Johan, we have time for a couple of questions.
Hi, yeah, thanks for the interesting talk. So if I understood it correctly, you really just start off with natural language as input.
Yeah.
Which makes me wonder, how do you prove the soundness? Is this an auto-formalization, or how do you make sure that you verify the correct function?
Yeah, that's a good question. So in the prompting, we only need users to provide us with the prompt in the natural language, but what model will give us is a domain-specific language. That's why we design the pipeline through checker and so on. And then after we get this domain-specific language, we can use an automatic verifier, and that verify soundness is totally based on this domain-specific language. It will translate it into several constraints and use the SMT solver to verify it, so that the verification is not based upon the natural language description.
So thanks for the talk. I assume your framework can generate the abstract transformers for any arbitrary neural network activation functions, right?
Yes, theoretically we can.
So basically for all the, for instance, like tanh dot product in the transformer architectures, you can also verify, right?
Yeah, so that's a good question. We showed that we can synthesize a lot of highly nonlinear functions in the slides, but actually we do manual verification and manual cost computation there because currently the SMT solver cannot support the constraints within the nonlinear computations.
But you can use the D-real solver to resolve
the
that,
D-real
right?
solver will have a relaxation strategy, the delta soundness. The delta soundness is not what we want because we require a strict soundness instead of some, oh, it might be sound, or within the delta it might be sound. That's not what we want. We tried that as well, though, but we didn't use that in the end.
Okay, but you remember that, so there is another work called DeepT, which it can also like generate sound bonds for, you know, for generating the abstract transformers for bounding the tanh function or whatever dot product in the transformer architectures. So I think they have proven their bound is sound. So I think it's along the same line of work.
I'm not sure whether I have read that, but I have read a similar work which also use that solver. But in that work, it will extra apply a relaxation strategy to ensure the soundness. But that will also cause some imprecision. So we think the best way here is just to do the manual verification, unless there is a better solver which can help us to do it.
But how do you guys do the manual verification? By using Lin and theorem?
No, we just manually derive write the bonds in a mathematical way and to verify it.
Okay, I see.
Yes.
Thank you.
Thank you.
All right, I think that's time. Thanks, Chuhan.
Thank you.
All right, while Shaurya is getting set up, our next talk will be given by Shaurya Gombar, also from UIUC, and he'll be talking about evolving abstract interpreters.
Hello, am I audible? Yeah. So hello everyone, I'm Shaurya, and now that we have seen how abstract transformers can be generated from LLMs, I am here to talk about what are some inherent limitations in current abstract transformers design and a new paradigm of abstract transformers called the evolving abstract transformers, which we propose to counter those limitations. So as we all know, abstract interpretation works by representing concrete states, a set of possible concrete states, using these elements in an abstract domain. Here, for instance, we have these shapes in the interval domain. And when you have to propagate these abstract elements through the program, you have these specialized functions. For here we have the intervals, the difference of the intervals, and these specialized functions are called abstract transformers. So there can be many abstract domains. We saw an example of the interval domain. Octagon domain has the intervals as well as bounds for the addition and the subtraction of variables. And then there is this polyhedra domain which allows you to represent state with arbitrary set of linear inequalities. And it's a known fact that as expressivity of the domains increases, this task of transformer design increases, the complexity of transformer design. And these complexity, the task of coming up with abstract transformers, like it has to do with three main things. First, the abstract transformer should be sound. So that means that the output abstract element should cover all the possible post states, and this is needed for the correctness of the analysis. The second thing is precision. So there can be many sound outputs, but you want to have as small outputs as possible for precision of the analysis. And efficiency, if you chase precision, then most of the times you end up spending a lot of time while computing a transformer. So coming up with or implementing abstract transformers is this task of always being in the sound space, but then this balancing precision and efficiency. So we identify three inherent limitations of this design, and I'll go through them one by one. First, the current transformers are per domain and per instruction. So what do I mean by that? There are, as we saw, many abstract domains. We just saw three, but there are like many infinite, like there are many abstract domains. And at the same time, there are many concrete instructions, for instance, assignments, meet with guard, guarded assignments, and so on. And coming up with abstract transformer means you have to implement a new transformer domain for a new abstract transformer for each domain and instruction. So this means that you have to spend a lot of time, or nowadays spend a lot of tokens to come up with all these transformers. And this results in these thousands of lines of complex implementation that are there in the current libraries. Furthermore, the current transformers are instruction specific. So what do I mean by that? If you see this two-line program, if you have to abstractly interpret this, currently for instructions, the transformers are implemented separately, and then while doing abstract interpretation, the result is composed. But it is a known fact that precision is non-compositional. So even if both those transformers are as precise as possible, the final result can be not the most precise. For instance, here, this block preserves this difference of x minus y. So if you see, in this block, x and y are both updated by y. But if you interpret it one by one, we don't see this captured. And so this requires sequence-aware abstract transformers. But as we have discussed, even coming up with transformers for single instruction is tough. But now we have these sequences, which makes it tougher, and also we have more things for which to design the transformers. Finally, we have this fixed precision efficiency trade-off. I'll spend a bit more time on that. So let's consider this example. And if you see in this example, initial value of x is 0. The loop body decrements x by 1. And so it's easy to see that x less than equal to 0 is a valid loop invariant. But when we analyze this program with the octagon analysis and using a state-of-the-art library, we see that this analysis is not able to prove the assertion. And when we investigate, we see that this transformer for x equals to x minus y is imprecise. Now, ideally, you would want to compute the most precise output at each step, but that is expensive. So consider this input for the abstract transformer and say we have to compute the most precise output for this case, and just focus on this bound. So this task requires, so the new value of x minus y is the old value of x minus 2y, because x is now updated to x minus y. So this task requires calling this LP solver to get this bound, and of course LP solver takes time to compute. And we have to do this similar time consuming task for 8 bounds here, and in general for octagons you need these O(n square LP calls for getting the most precise output. So current libraries do not do this, but they instead fall back to these cheaper and less precise heuristics. One of them is interval relaxation. So interval relaxation heuristics just ignores the relational constraints and just computes an interval relaxation answer. And the answer, if we observe, is sound, but it's less precise. And this imprecision that arises here propagates throughout the program, and that makes the difference between the assertion being proved or not. So essentially, what happened here was that the libraries prioritize efficiency over precision. But different tasks have different precision efficiency requirements. So if you have a task which requires this quick turnaround time, like a CI/CD task, then you might want to spend less time and be okay with the less precise answer. But like if your task is a safety critical task, like if you have to verify a program for some rocket that's going, then you'll be okay with spending more time, but would want more precise answers. And then there are these plethora of options in the middle. But as we have discussed, the current transformers have very fixed heuristics, and they don't allow you to adapt the analysis as per the task requirements. So having discussed all these limitations, what do we need? Ideally, we need a framework which works across domains and instructions, is sequence aware, and also allows you to adapt efficiency and precision. And here comes our evolving abstract transformers. So with evolving abstract transformers, we provide a unified framework that works across domains and instructions and sequences, and they allow tasks to adapt precision and efficiency by this idea of space of sound outputs, which we'll discuss in the coming slides. So on a overall, how does it work? Along with the element, it takes the instruction and the abstract domain for which to compute the abstract output. the first step is not to compute a single output, but instead compute a space of outputs. And this space of outputs has this property that for instance, this octagon family, all octagons which you can instantiate in this family are sound. And once you have that, you can use traversal techniques like gradient guided traversal to instantiate these. So if we see, like this technique works for, like this example was for octagon domain, but our technique supports all polyhedral domains, which are the domains where abstract state is represented using a set of linear inequalities. For instructions, our evolving transformers support all instructions which have linear updates, quadratic updates, and also meet operation with linear guard constraints. So this already gives us these two benefits, that now we have a technique which works for domains and instructions and is also sequence aware. Now we'll talk about how we solve this precision efficiency trade-off problem. So for this, our first key idea is instead of instead of computing this single output, for instance here, you should instead compute a space of sound outputs. For instance, like this green space is a space of sound outputs, and all the outputs that you instantiate, all the octagons that you instantiate from this space will always be sound. And once you have such kind of a thing, tasks can now adapt and pick outputs that suit them based on their needs. Now we'll discuss how can we capture such a space. So this is our running example, and we saw that to compute the most precise bound, we need to call an LP solver. But the key observation is that if x minus y less than equal to C sharp is the most precise, any bound which is greater than C prime results in a sound output. So our problem boils down to, can we get a space of bounds which is greater than C prime for this problem? And here duality can help us. So how does duality work? Like first we get these constraints into standard form, and duality works by introducing these Lagrangian multipliers for each constraints. And Lagrangian function is just with the objective, we multiply all the constraints with the Lagrangian multipliers and add them to create this unconstrained optimization problem. And Lagrangian dual is the maximization of the Lagrangian. And all this gives us this property that for all positive multipliers, this G lambda is greater than equal to C prime. So using this, we kind of have a sense of how can we capture this bounds, space of bounds which is greater than C sharp. But when we use this, the standard duality, the space of bounds which we get, the G lambda and the space, it's sound, but it's not very easily traversable. Because if you see, for this small case, we had 5 multipliers and these equality constraints, which makes it harder to sample from this space and also traverse this space. So our task is not only to get a sound space of outputs, but to get an easily traversable sound space of outputs. So that's why we come up with this selective dualization technique. And this is based on the observation that when we are doing abstract interpretation, in most of the abstract domains, we have these box constraints, which are just interval constraints on the variables. And the remaining constraints, we call them as the relational constraints. So in selective dualization, we dualize only the relational constraints. So we only introduce the multipliers for the relational constraints. And you can see this already gives us the benefit that we now have less multipliers. And now again, we construct the Lagrangian with these 2 multipliers. And now the interval constraints which we did not have the Lagrangians for appear in our Lagrangian dual. So they constrain the space on which we have to maximize the Lagrangian dual. And then using some specialized bounding procedures that we describe in our paper, we get this space, which again is sound. But if you compare it with the space that we would have gotten from standard duality, it has lower dimension, it has less number of constraints, and it has easier constraints. So now this space is easier to traverse than the previous. Before going to traversal, let's discuss about the properties of this space. So if you consider like this, and this G and the parameter space, and if we just sample some values from this parameter space and compute the bounds, you can see 5 examples instantiations here. So there are 3 properties that we see. First, all of them are sound because they are greater than -2. For 0, 0, the result matches the interval analysis result that we had. And also in our space of outputs, we had the most precise output. So in the paper, we formally prove these properties, and these properties are ensured by how we construct the space. Now, once we have such a space of outputs, the next step is to instantiate a concrete output from this space. Because when you are doing abstract interpretation, you can't just propagate space. Once you have this space, you have to pick one element. And here, ideally, if it was easy to pick the most precise, then we would have done that. But here, we instead need some search procedure in which the task can give us some search budget, for instance, R. And then the search procedure should be such that if we have more budget, then ideally we get more precise answers. So as we saw in our example, we don't get a bound, but we instead get this function, parametric bound. And the smaller the value, the more precise the bound gets. And our space is constructed in such a way that these parametric bounds, the space is always differentiable. So what you can do is you can allow tasks to give these gradient steps R. And if there is more time, then we can do more steps and eventually get more precise answers. But the issue with this is we can't just apply naive gradient descent because we also have some constraints that we have to satisfy. And if we do projected gradient descent sort of techniques, then they become inefficient because of the projection operation. So we come up with this adaptive gradient descent procedure, and it works like this. If we are inside the parameter space, then we can just minimize the bound to get more precise bounds. But as soon as we go outside the parameter space, we steer the search inside the parameter space by instead doing gradient descent on the violations. And because we had this property that at θ0 we have the interval relaxation answer, we can always start our search from that so that we are always as precise as interval. So pictorially, like the search starts from this interval relaxation answer. We take these gradient steps, keep getting more precise answers, but the time also increases, and we are fine with that. And as soon as the search goes into the space which is not inside the parameter space, for instance here, like the lambda1, lambda2 is 1.2 and 0, but we had this constraint that the sum should be less than equal to 1. Then at this point we descend on the constraint violation so that we can undo that, and we again go back to the sound space and eventually reach the most precise answer. So now, like doing this thing of computing sound space of outputs and efficiently traversing it using gradient descent also gives us this benefit of adaptable precision efficiency. Now I'll talk about our experiments. To evaluate, we used NLA DigiBench benchmarks. These are the state-of-the-art benchmarks for affine and nonlinear reasoning. They have these 55 programs, and across programs they have these 237 invariants. So we run our evolving abstract transformers with increasing number of gradient steps, and we evaluate two things. First, overall gain, this blue line. Overall gain is how many invariants got strengthened as compared to the baseline ELINA. And we can see here that as the number of steps increase, the number of invariants that get strengthened over the baseline increases. Similarly, this red line is, for this we computed the most precise outputs using an LP solver based approach. And here we compute that how many invariants are still not up to the optimal mark. And we see here that as the number of gradient steps increase, it eventually reaches 0. So that means we compute the most precise outputs for the linear case. We also compute this marginal gain, which just computes that when we increase the search budget from 1 to 2, 2 to 3, how many number of invariants get strengthened across that. A thing to note here is that when we run this analysis using LP solver baseline, that takes 230 seconds for zones and 350 seconds for octagons. But our analysis reaches there in 70 and 110 seconds, and this makes us around 3.2x faster also than these heavily optimized LP solvers. And that is because we do this gradient descent and jointly optimize the bounds. We also evaluate our framework on quadratic operators, and here we see that even for domains like polyhedra, we get these precision gains. So looking forward, we think that this framework can also be used for for many other things, like if it can enable GPU-based abstract interpretation, or if your task is to find some specific octagon to prove a property, then you can customize the loss function on which you do the gradient descent. Or while doing program verification, you can do some sort of abstraction refinement that if you see that your property is not proved, you can go back and choose a new parameter from the space. So yeah, this concludes my talk. And now we hope that after this, we don't have to implement a lot number of lines just to do abstract interpretation. And we have this one framework that can do abstract interpretation for many domains and instructions. And our paper and code can be accessed from the.
Thanks, Shaurya. We have time for one quick question.
Is there interest to go beyond like linear transformation, or like can you do it?
Yeah. So as I saw here, we do support the quadratic operators also, but that is because currently our bounding procedure supports linear and quadratic. Quadratic is easier because we can still do it by finding the root. We are also, there is this work in progress where we are also trying to extend this to polynomial instructions as well. What about?
What about exponential functions?
Exponential functions we have not yet thought about, but like if we have this support for polynomial expressions, then we can use Taylor series expansion for exponential functions and support it.
All right. Any more questions? Looks like not. Let's thank Shaurya once again.
Okay.
All right. The third talk of this session will be given by Xin Zhang, who's a faculty member at Peking University. Xin will be talking to us about how to do abstract interpretation with confidence.
Okay, thank you, Mukund. So this is a joint work with my students, Yuanfeng and Ziyue. Unfortunately, they couldn't come because of visa issue. So Yuanfeng is on job market and is applying for industry jobs. And Ziyue will apply to PhD programs in the US for the coming fall. So if you're interested, please contact them. So static program analysis has made great strides in the past decades. While they are typically sound, they are incomplete. As a result, they will lead to many false positives in some cases. And moreover, they cannot evolve on the fly with external information. To address these issues, an emerging trend is to build statistical models over these analyzers. Like one representative paradigm is called Bayesian program analysis. The idea is to attach probabilities to the rules. Now we can get confidence to the alarms. With the confidence attached to the alarms, we can do alarm ranking, filtering, and clustering. Moreover, by considering information like user feedback, dynamic information, outputs from large language models, we can now modify the confidence scores and do learning. Well, these kinds of work sounds very appealing. There's one question that has always bugged me. What do these confidence numbers exactly mean? Existing works have some answers, but the key question is, where does the source of randomness come from? When we talk about probabilities on confidence, the key is to define the sample space, which is the source of randomness. So some of this work attribute the randomness to the input distribution, but it changes the score to a different question. It basically asks, how possible can an input triggers the bug. But as we all know, for static analyzers, they really ask whether there exists an input that can trigger the alarm. So this is a different question. And some of this work, they just attribute randomness to historical observations of the alarms. But this disconnects from the semantics of the abstract interpreter. So this is also not what we want. And some of the works, they just don't have an explicit definition. So our paper tries to answer this question and draws a connection between the probability and abstract interpreters from theoretical perspective. To do this, we first define the source of randomness. Then we define the alarm confidence based on this. Moreover, we propose a set of denotation semantics to compute these probabilities. So in the rest of the talk, I'm first going to talk about definition, how we define the confidence. So briefly, the idea is that we are going to look at the execution of a given abstract interpreter and look for the distribution of the programs which can match this execution of the abstract interpreter. Then based on this distribution, we are going to ask how likely the alarm is true for a given program from the distribution. So this is a key idea of our paper. So after this, we define denotational semantics to compute the confidence. And in fact, we are going to introduce two semantics. The first one is a brute force one. And second one is a more tractable one, which underapproximates the original semantics. And finally, we are going to briefly talk about how we can do Bayesian learning with the proposed semantics. So let me start with the source of randomness. Here I have a very simple example, which is a sign analysis. So we can see the lattice of the abstract domain at the bottom. And at the top, we have execution of abstract interpreter. So what you see here is the interpretation of program which performs addition, no multiplication. So here the plus with the A at the bottom is basically the abstract transfer function for the plus operator. And then we have a positive number, which is denoted by z greater than 0. And the second command is similar. It's a multiplication between x and the positive number. So the question is that which programs can fit into this execution? Well, the answer is actually straightforward. So for any program which in the form like x assigned to x plus I, and the x is assigned to x multiplied by j, where I and j are numbers between 1 and n, they all fit into this abstract notation. And the result, we have a set of programs which can match this execution of the analysis. So once we have the set, we have the sample space of our randomness. Then the next step is try to attach a probability or measure to each point in this space. So how do we do it? Well, here let's just make the setup simple. Let's assume for both commands, they are independent and they are uniformly distributed between 1 and n. So any program in this space has a probability of 1 over n squared. And in reality, we can have more complex settings by learning from different sources. And our framework allows you to encode different probabilities. And we also support encode correlations between different commands in the framework as well, which I will get into briefly later. Okay, so why this makes sense? If we think about it, if I am an experienced analyzed user, whenever I see the execution of analysis, without looking at the program I can have an idea about whether the result is precise or not. For example, I know that when widening happens for some analysis, you are bound to lose some precision. So this is the intuition behind the modernistic kind of distribution. So once we have the source randomness, the next step is to define the probability of the alarms. Well, ideally, we want to define the confidence as how likely the alarm is true given the spec, right? That's really the ultimate goal. Unfortunately, we found that this kind of definition is not quite viable because if you want to compute such kind of probability, we didn't find any way except for enumerating all the programs in the space, which needs to know computational approach for computing it. So as a result, we turn into approximation. And the idea is that we are going to use local computers to provide lower bounds for the real probability. So what is the local computers? Well, the common computers we talk about is called global computers. It means that the abstract result exactly matches concrete behavior for every input set. And actually, this is too strong to guarantee in practice. And the notion of a local computer is that we are going to limit the comparison to a given set of input. And in some cases, you can just make the set as the domain of all the inputs, which is enough for many cases. So here is a brief comparison between the properties we'll talk about. Know that when we say inputs, we really mean all input sets. Okay, so once we have low computers, what we actually have is a lower bound of the probability of the alarm being true. Why? First, so if we talk about global computers, it's easy to say that even when analysis is incomplete, you can still derive true alarms, right? So the moment we talk about global computers, we're already talking about lower bounds. So further, when we go to local computers, we reduce number even further. So in some sense, what we have is a conservative lower bound for alarm truth. So in some sense, the confidence is defined through low computers. This is the approximation of the real truth we want. So let's go back to the example we just showed. Let's assume the input set only consists of 3 numbers, -3, -2, and 1. And the goal is to ask how likely the analysis is complete for this set. So if we look at the execution of the analyzer, the output will just be all possible integer numbers, because when we apply alpha function for the input, you get the domain of all integer numbers. And it stays as the domain of all integer numbers after 2 comments. However, if we look at which program can be complete for this abstract output, it is only complete when I equals to 2. Because when I is equal to 2, after the first command, you will have -1, 0, and 3, which covers cases for negative number, 0, and positive number. So you get all the possible cases for the signs here. And we say the probability of the analysis being low complete is 1 over n. So the next question is that how do we compute these numbers? To do this, we are going to propose 2 semantics. The first semantics is really an oracle, and it's not very practical. Okay, and the idea is actually very simple. So let's try to enumerate the distribution of the output sets of the program. So similarly, let's look at the same exam program with the same input states. So once we enumerate the possible output sets of the program, we can apply alpha function on each set I'll compare it with the output of the analysis and see if it's complete or not. The nice thing is that we can do this step by step. So when we process the first statement, so we can see that the post outputs can be summarized with this symbolic set. So basically, we add the number I to each input. And we can see that the probability for each possible output state after the first command is 1/n. So one thing I want to stress again is that the distribution is not distribution over a single output state. It's over a set of states. So once we process the first command, we continue the second command. And the way we compose these two together is actually straightforward. We just summarize over the intermediate states which lead to the same final states. And in this case, we have a probability of 1/n squared for each output states. So once we have output states, we just apply alpha function to each of them and see whether they match the expected abstract state computed by the analyzer. Well, as I said, this is really oracle, and it's not practical. The reason is that if you do this, you will quickly get exponential blow up as the summation grows. So we need a more tractable method. So how do we deal with it? The idea is that we are going to apply another approximation which is going to preserve the lower bound. And the idea is that at every step, we're only going to track the state which is locally complete at this point. So let's look at the example again. So after executing the first command, the analysis computes the domain of all integers. So if we look at all the distribution of the first command, we can find that only a subset of them are actually locally complete at this point. And for this case, only x is signed with x plus 2 is locally complete at this point. So this is the only state we are going to track. And in fact, for this program, we don't lose any precision. But imagine there are cases where the analysis is not locally complete at one point, but it gets recovered through certain commands later. Like one example is that you can multiply the number with 0, right? Then we just set everything to 0. And this gives another layer of a lower bounds approximation. Okay, and there are certain details I need to mention before I finish the talk. The first thing is usually the thing we talk about when we talk about the complexity of analyzers. How do we deal with loops? So to deal with loops, there's one we need to resolve, is that when you sample the commands from different iterations of a given loop, you have to maintain the same sample across the iterations. Otherwise, you will get an inconsistent program. So the way we deal with it is that instead of just tracking the output states, we're also tracking the sampled commands for certain kinds of instructions. The idea is that you only need to track the correlated commands. You don't need to track all of them. And this also gives us a way to express correlations between different commands in the distribution. And also to make the computation over loop trackable, the way we deal with it is to apply unrolling. The nice thing about unrolling is that it still maintains the lower bound probability, the lower bound property. The reason is that if you don't unroll fully, you just miss the cases being complete. So as a result, we can use the number of unrolling to balance the precision and scalability of our approach. And finally, if you want to do Bayesian learning using our semantics, it's actually quite straightforward. If someone gives you a negative feedback on a given alarm, you just throw away all the executions that don't meet the feedback. So to conclude, we formalize the confidence of a nice alarm, as a probability that a matched concrete program makes the abstract interpreter locally complete. And to compute it, we have proposed two semantics, one serving as an oracle, the other serving as a practical way to compute lower bounds of confidence. Thank you. That's all. Thank you.
Thanks, Shin. That was a really cool talk. Do we have any questions? Well, I have a lot of questions.
Okay.
The magic word that I didn't see you mention in the talk was measurability. You did mention a capital N though, and I was wondering, well, I would assume that ideally speaking, you'd want to talk about these in the limit as n tends to infinity, but then that would lead to division by division by infinity.
Yeah, that's a very good question. So in the paper, we assume finite measures, but in theory, we can handle with discrete measures, not continuous measures.
Do we have any more questions?
Do you have any empirical experience showing that your confidence scores can correctly filter out bad false positives? And
currently just a purely theoretical, no experiments. Okay. But that's what we want to do in the future. Thank you.
All right, I think that's time. Let's thank Shin once again. Do you have the microphone? Oh, Shin. So our last talk of the session will be given by Russell Abo, who's a PhD student at Berkeley. And he'll be talking to us about optimization and equality saturation. Sorry, optimism and equality saturation.
I didn't catch it, so you're fine. All right. Okay. Hi, everyone. My name is Russell Arbor. I'm a PhD student at UC Berkeley. Today, I'm going to be talking about my work, Optimism and Equality Saturation. This was joint work with my two co-advisors, Max and Alvin. So over the last few years, equality saturation has really been kind of rediscovered as this super powerful program optimization technique with a wide variety of applications, including floating point programs, tensor algebra, computer-aided design, imperative program compilation, RTL design, quantum circuit design, a whole bunch of stuff. In fact, I will point out that these last two applications in particular have seen very recent work, as in at this conference, and you should go watch their talks as well. I'm sure they'll be great. We got one in the audience. So naturally, this success motivates thinking about using equality saturation for more complex applications. So for my research, I'm interested in thinking about using equality saturation for, say, production optimizing compilers. Mentally, you can think of this as a state-of-the-art C compiler. Can we build one of those using eGraphs? Today, there are several problems that kind of get in the way of being able to do this. So in this talk, I'm going to focus on one of these problems, which is how to perform optimistic analyses inside of eGraphs during equality saturation. So first of all, what is an optimistic analysis? So intuitively, at a high level, you can think of an optimistic analysis as being an analysis that infers a non-trivial loop invariant about some data in your program with loops. So in this running example program, we have a loop that we have some variable x that starts at 1. Let's say x is an unbounded integer to make things simple. And each iteration in the loop, we add some positive number to x. So the non-trivial loop invariant we want to derive is that x is always at least 1, right? And standard interval analysis techniques, already in the literature, will indeed discover this fact on this program as written. And performing optimistic analyses is important in a production compiler because many programs indeed have loops, right? So the issue is that when we try to analyze this program in an eGraph using E-class analysis, it turns out that you will not discover that x is always at least 1. This is because standard E-class analysis, which is the way you do program analysis inside of an E-graph, is pessimistic rather than optimistic. So intuitively, this means it will not discover that non-trivial loop invariant. So for this program, it would discover that x might be any integer, which is not particularly useful. Additionally, if we try to make E-class analysis optimistic using standard program analysis techniques, and you're not careful and you do this in a naive way, you might actually derive unsound analysis results. So later in this talk, we'll see that a naive optimistic E-class analysis will derive that x is always 1 in this program, which is clearly wrong. So in this talk, I'll describe why this phenomenon occurs and how we address it. So first, I'm going to dig a little bit more onto what exactly I mean by optimism. So for ease of both analysis and for equality saturation, we view all programs as data flow graphs. So this running example program that we have, we can transform it into the data flow graph on the right. This graph is in static single assignment, or SSA form. You don't need to know the details of SSA form to understand the rest of this talk. I will just point out that the phi node in this graph, the one with the C label on it, corresponds to that variable x in the original program. And in particular, it corresponds to the cycle in data flow dependency that the original loop necessitates. We have to represent it using a cycle. So in order to perform an analysis on this graph, we can convert the graph into a series of analysis equations. Each analysis equation defines one variable. This variable is the abstraction for a node in the graph, and it's defined as a function applied to the abstractions of the inputs to that node. So these specific equations correspond to an interval analysis on the original graph. Now, these equations are mutually recursive, so we can't just pick some arbitrary order to solve them one by one. Instead, what we do is fairly standard, is we pick some initial assignment to the variables, and then we iterate the analysis equations until either a fixed point or a post-fixed point has been reached intuitively until the variables stop changing. Now, this initial assignment to the variables, so what is the initial assignment, matters a lot in terms of precision. So in particular, we can either initialize all the variables to be the largest possible interval, so negative infinity to infinity, or we can initialize them all with the empty interval, which we write bottom. We write as bottom. And depending on which of these initial assignments you use, you will get a different final analysis result. Now, these analysis results may differ in precision, but a core tenet of abstract interpretation is that both of these are sound. So if you look at, and you will see that both of these results are indeed sound, even if they differ in precision. Okay, next I'm going to describe some basics of equality saturation. So equality saturation is this program transformation technique where we can perform rewrites on a program without destroying the old program. So in particular, you store your program in a data structure called an E-graph, which remembers all the ways that I can express a particular value in my program. So the typical workflow is after you take a data flow graph and initialize an E-graph with it, I will run a bunch of rewrite rules that discover new ways of writing values in the program. And then after I've done this to my liking, I will extract a final program from it according to some cost function. Now, let's take a kind of simple example. If I have a program that consists of the two expressions on the left, I can convert this into a data flow graph on the right. All data flow graphs are E-graphs that are just trivial because no equalities have been discovered yet, or no interesting equalities have been discovered yet. We can apply a rewrite, which encodes the commutivity of addition, to discover that the two addition nodes in the E-graph are equal. We mark this in two ways. So one, we draw a red dashed edge between the two nodes. And then two is we change their labels to be the same. So in this case, now the two plus nodes are both labeled with C, which says that they're in the E-class C. And they're in the same E-class because they're equivalent. And then additionally, E-graphs can efficiently propagate congruence of functions. So the equality between the additions implies one new equality in the E-graph that we can discover. Now, during equality saturation, we may also want to analyze the nodes in the E-graph, or the E-classes in the E-graph, I should say. This is because some rewrites may be conditioned on an analysis result. So being able to analyze E-classes precisely may allow us to do more precise rewriting. Now, just as with normal data flow graphs, we can view E-class analysis as a set of equations. The difference is that these equations, each variable corresponds to the abstraction of a single E-class rather than a node. This is because any abstraction for an E-class is going to be sound for all the nodes in that E-class, because all the nodes are equivalent. That's why they're in the same E-class. Now, when I want to analyze two nodes in the same E-class, I can do that, and each node is going to have some transfer function that gives you the abstraction for that node in terms of the inputs to that node. When I want to get the abstraction for the E-class, I combine those analysis results. This means that as I perform more rewrites in an E-graph, my E-classes get larger. This means that my analysis of each E-class is going to get more precise, which may in turn allow me to do more rewriting, which in turn allows me to do more analysis, and this goes back and forth. Okay, let's finally return to the original problem. Okay, so consider this E-graph on the left. It's a very simple E-graph. It just represents the term 1 times 5, where I've applied the rewrite 1 times x is equal to x, because multiplying a number by 1 doesn't change it. So in particular, I put the times node and the 5 node in the same E-class. Okay, I can convert this into a set of interval analysis equations, as shown on the right. And if I try to analyze these set of equations, and in particular, if I try to do the optimistic analysis of this set of equations, I will actually arrive at an unsound analysis result. So in particular, my analysis will say that the E-class B can't be any value. It's in the empty interval, which is clearly false, because the original program, 1 times 5, is equal to 5. So something's wrong. Now, also notice that we can instead initialize all the variables with the largest possible interval, and that gives us the pessimistic analysis. And unlike the optimistic analysis, this one is sound, and in this case, it's also precise. And in fact, this is what existing E-class analysis systems do. They always compute a pessimistic analysis. So at least for this example, they will indeed compute an analysis that is sound. And in this case, it's also precise, so what's the big deal? Okay, let's return to our running example program. So we can convert this into a data flow graph. We can apply the same rewrite, because 1 times 5 is part of this program too. And then we can convert this into a series of interval equations. And we can do the same procedure. So we can perform optimistic analysis on this. And indeed, intuitively, because of that 1 times 5, we will still arrive at a unsound analysis result. Notice that this E-class C is analyzed as just being the interval 1, 1. This is what I meant earlier by saying that we will arrive at the result that x is always 1. We can instead perform a pessimistic analysis on this set of equations, but now we do not have a precise analysis result. So notably, this E-class C, which represents x inside the loop, it's in the interval -infinity to infinity rather than 1 to infinity, which is what we want. Now, it turns out that there is a solution to these equations that is what we want, which is that we find that x is always at least 1, but it's not obvious how to compute this solution to the equation. So in particular, what would I initialize all my variables to in order to arrive at this particular analysis result at the end? It's not at all obvious. So before we get into how we address this, I want to point out that there are 2 kinds of cycles in E-graphs, and this will be relevant. They are unfortunately not very well highlighted on the screen, so I will refer to them as the left cycle, which is the one between the phi node and the plus node, and the right cycle, which is between the times node and the E-class B. So that left cycle corresponds to the loop in the original program and corresponds to an actual data flow dependency cycle, while that right cycle corresponds to, or rather it was created by this rewrite, 1 times x gets rewritten into x, and does not correspond to a loop in the original program. What it instead corresponds to is that 5 in the E-class B is equal to 1 times 5, and 1 times 1 times 5, and so on. In other words, I can multiply 5 by 1 any number of times, and I'll still have 5. Unfortunately, this also corresponds to the program 1 times 1 times 1 times 1 times 1, and so on, or x equals 1 times x, which either way you say it is not particularly well defined, but we still analyze it. For more details on what I mean by represent, I encourage you to take a look at the paper. Also, I'd like to point out that this original observation that E-graphs have these 2 kinds of cycles, I should credit Sam Coward, Cheng Zheng, and Alexandra Silva. They first noticed this, and this work builds off of that observation. So as we saw before, optimistically analyzing the right cycle is problematic. It produces unsoundness. But we want to optimistically analyze the left cycle for precision reasons. So the crux of the optimistic E-class analysis algorithm that we will describe is to treat these kinds of cycles differently. So just to give another name to these kinds of cycles, the one on the left that corresponds to the loop in the original program, I will call well-formed. And the cycle on the right, which was created by this rewrite and does not correspond to a loop in the original program, ill-formed. Okay. Now, I will actually describe the algorithm. So first, what we're going to do is we're going to notice that the well-formed cycles in this graph are exactly the data flow cycles that are encoded by loops in the original programming. That's how we defined well-formedness versus ill-formedness for these cycles. So we are going to identify these cycles with constituent what are called back edges. These are edges going into phi nodes that correspond to iterating a loop in the original program. So in this diagram, the blue edge is the back edge and corresponds to defining a new value of x in terms of the previous value of x in the previous iteration of the loop. Next, we're going to compute a pessimistic analysis on this E-graph while ignoring this back edge. Intuitively, this is conducting analysis that is going to be sound, assuming that loops never execute once. So notably, this is not all program executions. This is only program executions where loops iterate at most once. Now, I will point out that because this is a pessimistic analysis, it is indeed sound. So in particular, the ill-formed cycle does not poison the analysis result. So the analysis result will be sound for this subset of executions, but it is sound for that subset of executions. Next, we can, so I should also point out that this is where the optimism in the algorithm gets inserted. So although at each step of this algorithm we're computing a pessimistic analysis, the optimistic assumption is this original version of the analysis where we're assuming loops execute at most once. Okay. Next, we're going to compute an analysis result that's sound, assuming loops execute at most twice. And the way you do this is you do exactly the same thing. You perform a pessimistic analysis of the E-graph. But along back edges, you can use the result from the previous iteration. So we can use results from the pessimistic analysis, assuming loops execute at most once. And then we can repeat this k times to get an analysis that is sound, assuming that loops execute at most k times. Okay, then this outer process we repeat until a postfix point has been reached. So intuitively, we repeat this until the analysis variables for all of our E-classes stop changing. At this point, the analysis is sound for any number of loop iterations, so for any program execution. And at this point, finally, we have a result that is sound totally for any execution. Okay, so I encourage you all to take a look at the paper for more details on how to interpret cycles in E-graphs, more details on the proposed algorithm and its proof of soundness, more details on how to integrate optimistic E-class analysis into equality saturation, and empirical performance results. And with that, I'd like to thank you all for listening, and I'd be happy to take any questions.
Thanks, Russell. We have plenty of time for questions.
Would a recursion bring some problem of computing the fixed point?
Sorry, can you say that louder?
Would a recursion bring some problems in your computation?
So the way we formalize this for this paper is we just deal with control flow graphs in a single function.
A single while loop, right? But if it's like different levels and all that.
So you could have nested while loops. That we handle that fine. But the formalization is for a control flow graph in a single function.
So what about probabilistic program? Do you think do you foresee that it's possible to generalize it? It seems to correspond to some complicated.
I am nowhere near an expert enough in probabilistic programming to answer that.
Hi, Tom Ball, University of Washington. So those two loops, I mean, the second one on the right-hand side's really just an equivalence class, right? It's not really a loop in any sense that I look at it. It doesn't, so I mean, duh, you should treat them differently. I mean, I don't really understand why you would call that thing on the right a loop. I mean, this is just maybe nitpicking, but that's an equivalence class, so you
I mean, in some sense, I agree. And the point of this work is kind of to bridge the gap between the mechanics of the E-graph and what we intuitively know to be true. I agree intuitively, that is not a loop. That doesn't correspond to a loop in the original program.
But it was treated as such somehow in your transformation into data flow analysis.
So in particular, Yeah, so in particular, so I should also emphasize, the way we formalized E-class analysis, this is standard. We did not do anything weird there.
Right.
Prior work formalizes E-class analysis equations in the same way. So the first contribution of this work is to point out that this weirdness happens. And it's a how should I phrase this? It's a facet of the prior work and how E-class analysis is formalized.
I see, okay, thank you very much. Yeah, cool stuff, thanks.
Hi, Xianyang from Colombia. So yeah, eGraph is great, and so I wonder how much benefit can you get when applying such an optimism eGraph analysis when in real world eGraph compilers or optimizers? Yeah.
Yeah, so this is something we did not evaluate to the extent that I would like in this paper. This is something I'm interested in continuing to evaluate. So in this paper, we just mostly focus on the theoretical aspect. That being said, I think it's kind of hard to evaluate this right now. And it's sort of a chicken and egg problem because there's not really a eGraph-based compiler that handles a complicated language with loops or recursion or that kind of thing yet. I think because we don't have the capabilities to properly handle them yet. So I think we will be able to answer that question once we have the capabilities to then build the thing, to then empirically evaluate how much it helps.
Okay, thank you.
I have a question. So for example, as it was on the screen, so there was example, for example, b equal to 1, then we assign b like different values. So as I understand, we solved this problem in eGraph, and I have a question. So there's still kind of trace of modifications that happen to B before we separate them, kind of. Do we just lose track of all those traces, or we still can optimize them?
Sorry, I'm not sure I understood the question.
Yeah, so for example, B is mutated multiple times during evaluation. So with this new approach, on the traces of these mutations, they're getting lost, or they still, for example, can be somehow optimized?
So one aspect of SSA form that I didn't go into the talk is that, let's see, way back, how far back? Let's see. Yeah, so the program on the left has mutable variables. So there's this mutable variable x that gets mutated multiple times in the loop. When we convert it into this data flow graph, and when we do a process called SSA translation, this graph on the right, you can define semantics for it without having mutable variables. And this is the standard way of dealing with programs in eGraphs. You usually don't talk about variables that mutate. You instead talk about definitions of values that are immutable.
Okay, got it. Thank you.
Hi, this is Byron Zhang from University of Chicago. So at each step of your iteration, when you remove the back edges, in the graph, do I get a DAG? Do I get an acyclic graph then where I can just do a topological traversal? And
not quite. So if you ignore this blue edge, right?
Yeah.
There is still a cycle. It's the bad one. So that means, and this is why, by the way, so if you look at E-class analysis implementations, it's not a single pass over the whole eGraph. This is why. Because there are still cycles. They're not usually that helpful, but they still exist, and you have to deal with them.
I see, but for these cycles, because we know that they're in the same E-class, wouldn't it necessarily mean that the value will be the same?
So you can make more complicated examples where the cycle spans multiple E-classes.
Right, okay. Thanks.
Just to actually make this concrete, imagine I have a program, x equals something, y equals x plus 2, and then z equals y minus 2.
I see.
You will get two E-classes, and there's a cycle between the two.
I see, but it's not, they're not all equal to each other, but you have a middle.
Exactly.
Intermediate right in the middle. Thank you.
Hi, good talk. Awil from UIUC. I did not understand what does this algorithm or this whole analysis have to do with eGraphs in specific. The whole thing can be applied to general abstract interpretation to general program analysis also.
I agree. I think the reason, the motivation for it is specifically eGraphs, right? Because of this, the ill-formed cycles that happen due to rewrites in the eGraph. And they are an artifact of performing these non-destructive rewrites in the eGraph. So in particular, there are some variants of eGraph systems where a rewrite such as 1 times x goes to x would not keep 1 times x around. Intuitively, because who cares about 1 times x, right? But there are, that doesn't cover every case, but in such systems, you would not get this cycle. You would just get 5 instead of the times node for the E-class B. So I would say you could apply this algorithm to any data flow graph. It's just that maybe the motivation for it is specifically the E-graph.
Thank you.
Thanks, Arjun. Let's take the remaining questions offline. It's time now. Let's thank all of the speakers once again.